Yeah, welcome, Dr. Arun. So, am I audible?
You are audible. Can you give me 5 minutes? Like I have to.
Sure, sure.
Okay, thanks.
Yeah, okay.
Fruits, food, far, water, soda.
I'm ready now. Yeah.
We will just give a brief introduction. After that, you can join. Yeah, Swarnima, you can introduce the guest.
Hello, thank you, sir. Good evening, everyone. Welcome all for the second day of ATAL FDP workshop. I am Swarnima, your host for today's session. Today, we will be having a great session by Dr. Arun, who has completed his master's from NIT Calicut and doctoral research from IIT Madras. He did his postdoctoral research at Duke University and is currently serving as assistant professor at IIT Guwahati. He has authored numerous papers in top journals and conferences. He has also won multiple grants from the Government of India. We heartily welcome you, sir, for the session. Sir, you're mute.
Yeah. Yeah. Okay. Thank you for the introduction. Uh,
You have again gone on mute. Dr. Arun, you're again on mute.
so am I audible?
Yeah, you're audible. Yeah,
Uh,
yeah.
Sir,
yeah. Okay. Thank you for inviting me for this talk. And so today I'm planning to talk about quantum error correction codes. I will plan to introduce quantum error correction codes from the perspective of classical error correction codes. That is my objective of the talk. And so I like to go with slides, and so instead of slides, I like to go with this notepad. So if you are not convenient, let me know. Okay. So my plan is to go with notepad. Is that fine? Like, so whenever it is required, we will go through slides, and whenever in other cases, we will go with notepad. Okay. So can I share my screen?
Yeah, yeah. I have made you presenter. You can share.
Okay. 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 So is that fine?
Yeah, your screen is visible. Yeah.
Okay, fine. So yeah. So yeah. So so I hope most of you may be from a classical background. Like, so that is my assumption of. So the assumption that I make before starting the program is so assumption is most of them are from ECE background. So that is my assumption. Okay. So BECE background with the zero quantum knowledge. So whether my the writings are readable, is that fine?
Yeah,
Yes,
yeah,
sir.
it's readable. Yeah, yeah.
Yeah. So if it is not readable, let me know. Okay, I will try to change the font size or something. Okay. So this is my assumption. Okay. So and the goal is introduce quantum error correction from a classical perspective. Okay, so along the lines, I may introduce what qubit is and so on. So that is the plan for the today's talk, the first session of the talk. Okay. So first of all, why quantum error correction? So why should we wanted a quantum error correction? So the biggest challenge in both classical computers and quantum computers is noise. Okay, noise is the biggest challenge here. So now to overcome noise, we can have several things. So classically, we try estimation techniques, right? And our other thing is we add redundancy, which can help us in noise control. Okay, so this estimation techniques, this one is something called as error mitigation. So if you wanted to look into the estimation technique in quantum error correction to reduce suppressed noise, you can look into this topic called quantum error mitigation. Okay, so we are not going to talk about quantum error mitigation for now. So for people who are more interested in estimation related theories, they can focus on quantum error mitigation. Okay. So in today's talk, we will talk about redundancy. Redundancy, we add codes, or this one is called as channel codes, right? So channel codes. So we will focus on this channel codes. That is what we will plan to introduce. Okay. And so now we try to control noise by adding redundancy. That is the idea. And this is more effective, highly effective in the large scale sense. Like, so if you wanted a highly reliable quantum computer, then I should go for this error correction code. So I cannot rely on estimation or error mitigation techniques for a perfectly reliable computers. So this one, people use it for this small scale quantum computers or medium scale quantum computers. Okay, so this is immediate. So if you focus now, like people, so if you see the recent hardware, the recent algorithms that people implement, they as a first step, they implement error mitigation, okay, for a small scale quantum computers. And now for error correction, this noise control to work better, so we have to go for redundancy. That is, you have to go for channel coding. Okay, so that's why in this course we will focus on channel codes. Okay, or so we will use the term error correction codes. Okay, so error correction codes. Yeah. Is there any question? It's not audible. It's not properly audible. Is there any question?
I think that's noise, sir. You can
Okay.
continue.
Sorry. Okay. So we will talk about the error correction codes now. Okay. So as a introduction, I will start with classical error correction code. What we do in classical sense. Okay. So what we do in classical sense. So classically, I wanted to protect my information. So normally the simplest error correction protocol that we think about is, so I wanted to send 0. So instead of 0, I will encode it in the sense of you repeat 0, 0, you repeat the 0 3 times or something like that. So or n times. So this is called as repetition code, right? So, and if you want to encode 1, you send 1 1 1. So this is the standard repetition code. Okay, that we do in classical sense. And now suppose I wanted to where is it? Okay, so suppose I wanted to check whether there is a noise or not. So I transmit 0. So for example, I received 0 1 0 because of noise. So noise corrupted my data and I got 0 1 0. Now I wanted to check whether there is an error or not. So what I will do is, so assume that is, I call this as C0, C1 and C2. C0 represents first bit, C1 represents second bit, and C2 represents third bit. So whatever I will do is, I will try to do C0 plus C1. So I will check whether this is 0 or not. And similarly, I will check C1 plus C2. I will check whether it is 0 or 1. And this addition in the sense of binary addition. So this plus is binary addition. Okay, so binary addition, people with logical gates perspective, you can recall this exclusive OR gate. So this is what the binary addition means. Okay. Okay. So there is something that troubles. So now this is our focus. So we have to check our errors. Okay. Okay. So we have, so suppose we have some errors, we will check these two conditions, whether C0 plus C1 and C1 plus C2, and we will check whether both are zeros. If you note these two codes, these two are proper encoding. So if you try to add C0 and C1 or C1 plus C2, that is equal to 0. So if I get if I get this summation as 0, we call it as a perfect code. Like we say that there is no noise. And if it is 1, if any of this summation is 1, then we call that there is some noise. Okay. So in this case, we have C0 plus C1 equal to 1, and C1 plus C2 is also equal to 1, which means there is some noise. And with this information, we try to detect whether there is noise or not. Okay. And a different way of representing this is, so maybe I will open a new page. Okay. I will zoom it up to. So a different way of calculating this is, so I have C. Okay, what happened to this? 1 minute. I apologize. Like, so I will check my pen once. So I couldn't make it. Okay, I will try to write this and see. Okay, so I have this message. I have this code word C0, C1, and C2. So the simplest thing that we normally do is we put it in on a vector, and to have a parity check equation, we construct these equations. So in this case, we make 1, 1, 0 and 0, 1, 1, and this will be exactly equal to C0 plus C1 and C1 plus C2, and we will check whether this is a 0 vector or not. So if it is a 0, we call that no noise. And if it is not equal to 0, then we say that there is an error. And this term is called a syndrome. Okay. So generally what we do is we received some R, that is this one in this case, and we multiply with a matrix H, which is this parity check matrix, and H times R will be called as syndrome. Okay, and this S will tell us a lot about the more information about the noise. So if S is 0, then no noise, and S is 0, 1, we say the bit 3 is flipped in this case. And if it is 1, 1, we say the bit 2 is flipped. And if it is 1, 0, then we say bit 1 is flipped. Okay, and S equal to 0 implies no noise. Okay, so that is how we check errors in the classical computers. Yes. Okay. Okay. So I think it's another again noise. So we will talk about this parity check matrix further. And another example of parity check matrix is this one. So you have 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, and 1, 1, 0, and 1, 1, 1. So this is another parity check matrix which represents a 7-bit code. Okay, so this one is commonly called as Hamming code. Okay, so we will talk about these two codes, and we slowly generalize it into the quantum version of these two codes. Okay. And the next thing is we have to talk about quantum version of it. So when we introduce, so to introduce quantum version, the first thing we have to know about is what is a qubit. So instead of bits, we are going to use qubits here. So whatever bits in classical, so bits in classical, so we'll go to qubits in quantum. Okay. So how do we represent as a qubit? So an arbitrary qubit we normally represent by this ket notation, ket psi. So arbitrary qubit will be of form alpha times 0 plus beta times 1. And this can be represented in a vector form where you write it something like this. Okay. So this is how we have an arbitrary qubit. And now the second thing is we have to talk about operations. So mostly we talk about unitary operators. Those are the operators that we can do it on a qubit under the controlled environment. So as long as there is no external disturbances, so all these operations acting on qubit can be represented by something called unitary operator. U times psi will be something, it's some unitary operator. So we will talk about those unitary operators. A specific class of unitary operator is called Pauli operators. Okay. So this one is identity, which you don't do anything, and X, which is flips your bit. So what does X does? X acting on ket 0 will be ket 1. X acting on ket 1 will be ket 0. So this is what it does. Like it's a classical bit flip operator. And you have a Pauli C, which is normally, 0, 1 and 1, 0, which is normally represented as 1, 0, 0, minus 1. So C acting on 0 will give you 0, and C acting on 1 will give you minus 1. Okay. And apart from these two operators, there is one more Pauli operator, which we call it as Y operator. This is normally I times X is it. In this talk, we will try to avoid Y. We will focus on I, X, and C alone in this talk. Okay. And this X and C has an interesting property, that is, if I try to take X times C, this is exactly equal to minus C times X. This is what going to help us. Okay. So in quantum sense, you have an arbitrary qubit can be represented by this, and we have unitary operations. All these are single qubit operators. So one is bit flip operator, which is X operator, and another is phase flip operator, which is C operator. For now, we don't talk about the Y operator, which is a mix of bit flip and phase flip operator. Okay. And so there is one theorem which states that if you can correct errors A and B, you can if A and B can be corrected, then any error alpha times A plus beta times B can be corrected. So this is one important theorem. Like, so if you can correct any two error operator A and B can be some unitary operator or some other operator, some random operator, which means you can correct any linear combination of A and B. And this is the crucial, because if you can correct I, X, Y, and C operators, so if you can correct, if these are correctable, this implies you can correct any 2 by 2 error, any 2 by 2 unitary. That is because if you take any unitary 2 by 2, it can be written as linear combination of I, alpha 0 I, alpha 1 X plus alpha 2 Y plus alpha 3 Z. So any unitary operator can be written as linear combination of Pauli operators. Because of this, we need not, whatever maybe our error is, it can be arbitrary unitary operator or something else. But if you are able to correct these 4 errors, like identity is no error, and X, Y, and C error, then you can correct any single qubit error. So that is the idea of this theorem. And similarly, a 2 qubit generalization is, it can be combination of II, XX, YY, ZZ, and so on. Okay. So if I think about 2 qubit combination, we can talk about x2, where x acting on second qubit and identity on the first qubit. Identity on the first qubit, x acting on the second qubit. And similarly, x1, x acting on the first qubit and identity on the second qubit. So these are different operators that comes into our picture here. Okay. And the third important property is measurement. Okay. So the problem is, like, now you have a quantum state which is psi, which is alpha times 0 plus beta times 1. Now suppose someone go and try to measure this quantum state. So what they will end up getting is either 0 or 1. The state collapses. And once I receive 0 or 1, my psi will, after this, my psi will be updated to 0 or 1, depending on the outcome. So you are going to, you will be able to measure either 0 and 1 and not the superposition of 0 and 1. And once you measure it, the new state gets collapsed to the 0 or 1. So that is the that is one challenge here. And this one is something called as orthogonal projective measurements. Orthogonal measurements. So in talk we will focus on orthogonal measurements because they can be more optimal measurements. There are other measurements which are non-orthogonal measurements which are called as POVM, which we need not worry about it in this talk. Okay.
Sir, I have
So
a
we will
query,
focus
please.
on, yeah.
You just
Yes,
wrote
please.
you just wrote that once it is measured, the quantum state collapses, and hence it can be either ket 0 or ket 1. So my
Yeah.
query is, if the quantum state collapses, then it should be classical output 0 or 1, not ket 0
Yeah, it
and
will be
ket
classical output 0 or 1. Yeah. So
just
yeah,
wanted
when
to
I
clarify.
mention 0 or 1, it can be a quantum state 0 or classical state 0. This quantum state is classical. Like so suppose I wanted to encode a classical 0 and classical 1, we usually can encode it in this form, 0 and 1 in a quantum state. Okay. So that's why when I mention just ket 0 or ket 1, we can assume this as classical state. Okay, that's just a notation, like notational convenience.
Okay.
You
All
can
right.
think
Thanks,
of this
sir.
as a classical state. If you are confused, you can think of this as a classical 0.
Yeah, I
and
just got confused. Yeah, that's fine. Okay, thank you, sir. Thank you.
yeah. This is classical state, exactly. Yeah.
Okay.
But this one is classical, but this is a classical state, but this one is a quantum version. Like the notation is quantum, you cannot change it. Okay, it's called post measurement state. Once you measure it, the state collapses into either 0 or 1. This is quantum state, but then it's a valid classical state because classically we can separate 0 and 1. Even in quantum sense, you can separate the 0 and 1. You can measure that separately. So the thing is, if I try to measure the state 0, I will get 0. I won't get anything else. And similarly, if I measure 1, it will be 1. And it behaves as similar to that of a classical state. Okay. And yeah, so before that, one more important property of this is, so classical error correction code mostly relies on copying the qubits. Okay. Sorry. So classical error correction codes mostly rely on copying a qubit. Okay. The challenge here in quantum error correction, quantum computing is you have something called as no cloning theorem. So what does it say? If you have a quantum state psi, and if you wanted to copy the state psi, that is, you take a copy of state psi, which is not allowed in a quantum state. And the key reason for this is that the operators are linear operator. That is, copying is not a linear operator, to be specific. How do we copy? You take an arbitrary state psi and you attach with another state with a buffer state, and you apply some transformation on it, and to get the state copied in the new state. But this one, because this operator is linear operator, this one will not go ahead. Like, so you cannot copy this. So you can try it out. So I am not going into the details. Apply alpha 0 plus beta 1, and you will end up getting that this can be done only if alpha equal to 0 or beta equal to 0, which means it's a classical state. If alpha equal to 0 or beta equal to 0, then it's a classical state exactly. Alpha equal to 0 implies ket psi equal to 1, and beta equal to 0 implies ket psi equal to 0. So these are the classically identifiable states. Okay. So quantum states cannot be copied. So that is the main challenge here in our error correction codes. So what we do, the challenge, what we do in classical error correction codes, when we have a bit information 0, we normally convert it into 0, 0, 0, and when we have a bit information 1, we converted it into 1, 1, 1. This is the very elementary level of classical error correction code, which is repetition code. But the problem here is, if you take a quantum state psi, you cannot do this psi, psi, psi. This is not allowed because of no cloning. Okay, so to overcome that, so we have to do some trick. So one of the thing that we normally do is we encode the classical state, the 0, as the classical repetition. 0, 0, 0. That is, I could repeat 0 3 times. This is exactly same as having the first qubit 0, second qubit 0, and third qubit in 0 state, and classical 1 in 1, 1, 1 state. So this will be 1, 1, 1. Okay, so you repeat. So the classical 0 is repeated thrice, and classical 1 is repeated thrice. But when it comes to arbitrary superposition, if we take alpha times 0 plus beta times 1, now I am not going to repeat the state thrice. Instead, what we will do is alpha times 0, 0, 0 plus beta times 1, 1, 1. So you repeat the classical states, but not the quantum state. So when the repetition in the classic quantum state depends on the repetition in the classical state. So this one is something called as entangled state. For now, I am not going into the details of the entanglement, but this is an entangled state. Like, so you have somehow entangled the first 3 qubits in some sense. Okay?
So just a doubt here. So the resulting vector will be a 8 element vector.
Yeah, this one will be a element vector. So you have so if I take,
can you just write down the letter? Can you just write down the column vector?
Yeah, I will try to write it down. So the thing is, how this encoding is done, you have alpha 0 plus beta 1. So we normally add 2 buffer states, and these are hidden in the classical repetition code. Like, so classical repetition code also, we have this information qubit and encoded in the redundant qubit. Similarly, we have the information qubit, we add some redundant qubit, and we convert it into alpha times 0, 0, 0 plus beta times 1, 1, 1. This is in vector form. This is nothing but in terms of 0, 0, 0, you have alpha, and you have 0, 0, 0, and then beta 0, 0, 0. This is your this state, and this one will be, so you convert this into alpha, and again 6 zeros and beta. Okay, so yeah, so maybe I will introduce what a 3 qubit state is like. So if required, like, so the 3 qubit states, in 2 qubit you have 0, 1, right? And 0 is represented as 1, 0, and 1 is represented as 0, 1. This is the idea. So that you have alpha times 0 plus beta times 1 becomes alpha times 0 plus beta times 1 becomes alpha and beta. So this is how the class the single qubit works. Okay. Similarly, if I go for 2 qubit, we have 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So this 0, 0 can be represented as 1, 0, 0. So we have 4 different options. So which means I wanted a vector of length 4. So 0, 0 can be represented as 1, 0, 0, 0, and 0, 1 represented as 0, 1, 0, 0, and 1, 0 represented as 0, 0, 1, 0, and 1, 1 represented as 0, 0, 0, 1. Okay, right? So with this notation, so when it comes to 3 qubit, we will have 0, 0, 0, 0, 0, 1 up to 1, 1, 1. So we will have 8 different options here in terms of binary, right? So our vector will be of length 8. So now to represent 0, 0, 0, I represent 1, 0, 0, 0, and all the remaining terms are 0. Okay, and goes on. For 1, 1, 1, it is all the remaining terms are 0, and at the last unit will be 1. So this will be, these are the basis vectors. Okay, and one interesting fact about this is, maybe I will try to go to the new page. So one fact about this is, now if I take the 0 vector, 2 qubit state, so I have 0, 0, 0, 1, 1, 0 and 1, 1. Now 0, 0, this vector form will be something like this. And this has a nice pattern, like, so I can write it like 1 times 1, 0, 0 times 1, 0. So I can write something like this. So 1 multiplied by 1, 0, so you get 1, 0. And 0 multiplied by both, you get 0, 0. So you can write it something like this. And this one can be represented as something called tensor products. So I'm not going into the details of the definition of the tensor product and so on. So this is represented as some tensor product. So roughly it is like I extract. So since these two vectors are same, I put that vector separately, 1, 0. And I put the remaining terms separately here and added the tensor product notation in between.
Yeah, no problem. I have told them in the basics this thing I have told. So no problem.
Okay, so this is 0, 0. And similarly, 1, 1, 1 will be something like, so if I have, yeah, so we have alpha 0 plus beta 1 will be mapped to alpha times 0, 0, 0 plus beta times 1, 1, 1. So if I take this one, the map will be alpha times 1, 0, 0, 1, 2, 3, 4, 5, 6, 4, 5, 6, 7, 8 plus beta times 1, 2, 3, 4, 5, 6, 7 and 8. So you will have this. Okay, this will be the vector form for this alpha 0, 0, 0 plus beta 1, 1. Okay. And now the most crucial thing that I wanted to highlight is how this can be encoded. So how can we do this encoding? That will give you the connection between the classical coding and the quantum codes. So how can we do the encoding? So now you have this, you put up your state on the first qubit, that's it, alpha 0 plus beta 1, and you initiate 2 new qubits, that is initiated at 0. What I do is, you have a control NOT gate, okay, and 2 control NOT gate. And this control NOT is a gate. What does it do? So if I have 0, 0 here, I will end up getting 0, 0, and 0, 1 will be translated to 0, 1, and 1, 0. Whenever the first qubit is 1, you apply a NOT in the second qubit, which means it will be translated to 1, 1. And similarly, 1, 1 will be translated to 1, 0. This is the control NOT. But the idea is, whenever the first qubit is 0, like whenever the first qubit is 1, you apply a NOT gate to the second qubit. So whenever apply a X gate to the second qubit. Whenever the first qubit is 0, you don't do anything in the second qubit. That's the idea. So if I have a circuit like this, this outcome will be alpha times 0, 0, 0 plus beta times 1, 1, 1. Okay. So now the next challenge that we have to face is, so how are we going to correct the errors? So the problem here is, suppose you have some quantum state and you try to measure something, your quantum state is going to be destroyed. So it will become a classical state. But in this kind of things, the advantage here is your information is in the first qubit. And second qubit and third qubit are redundant qubit. So whatever happens there, it is not a problem for us. And that's what we are going to utilize. So whenever we have a noise, we are trying to capture using these 2 qubits. So how are we going to capture it? So we try to see the operator that does not affect this qubit. So for example, in this case, if I apply C times 0 will be equal to 0. So the quantum state 0 is unaltered by the C operator. Okay, so that's how we defined it, right? So now if I apply a C operator here, the state is unaltered. Okay, now the challenge here is, we are not going to see here and try to measure C. We wanted to see what is equivalent of C in this region, okay, what is this equivalent of C on the second qubit in this region. Okay, and this is one interesting property about C0 gate. So if you have a C gate here, if you have a C operator here, and this is equivalent to having 2 C's here and here. Okay, so which means, so my C on 2 second qubit, after this 2 C0 gate, at this point, so this C on second qubit is translated as C on first qubit times C on second qubit. Okay, and identity on the third qubit. So normally that is something that we don't worry about it. So I don't mention it. Okay, C on first qubit and C on second qubit. And similarly, we have one more ancilla qubit, this third ancilla qubit, that is C3. This will be translated as, because of this C0 gate, that will be translated as C1 times C3. Okay. And now we can clearly see what happens to C2 times C3. This can be translated as C2 times C3, right? So there is no change here. Like, so C2 times C3, so you can take the product of these two. Product of these two, same as product of these two. Okay. So the idea is, now you do measurement on this operator, that is the C logical operator on this thing, or you do measurement here with respect to this translated operator, your information is not going to be affected. Okay, so that is the catch here. So that is what we are going to do. So yeah, so before that, I have to clarify what do we mean measuring by this operator. So measuring by some operator P. Okay, you have a quantum state. Okay, now we will focus on all Pauli operators. So whenever in this stabilizer codes or whatever codes that we are going to talk about, all these are Pauli operators, which means these Pauli operators will have a property like P times psi will be equal to psi, or P times psi will be equal to minus psi. Okay. Oh, sorry. So you take a quantum state psi, you apply some Pauli error, right, and apply P times E psi, and this will be equal to either E times psi or P times E times psi will be equal to minus E times psi. Okay, so one of this usually happens. Okay, so the idea is here we have C operators, and we are going to correct the errors that are corresponding to X operator here. So X times 0, that is an error, it translates to 1. Okay, X2 on 0 will be translated to 1 on the second qubit. And now the equivalent X on the other side will do something to the state here. The X2, that will be translated to something here. Okay, and that particular error is what we can correct. And similarly, X2 on this operator can be translated to something here. That particular error can be corrected. Okay, and if you observe this, okay, maybe. So if you observe this, X2 is translated to X2, and X3 is translated to X3. And if you think about X1 is actually translated to X1, X2, X3. So this is one small issue. Like, so if I take the first qubit, so in this particular circuit, so you have the error on X2, that is translated as error on X2, the qubit 2, or single qubit error on qubit 2. If you have an error on X3, that will be translated single qubit error on the third qubit. But suppose you have an error on X1, the first qubit, and that will be translated as X1, X2, X3. And if you notice carefully, you take the arbitrary quantum state alpha 0, 0, 0 plus beta 1, 1, 1. You take an arbitrary state. Now, if you apply an error X on the first qubit, so alpha times, so X on the second qubit, alpha times 0, 1, 0 plus beta times 1, 0, 1. Now you can see that the repetition can be recovered. So you can find that, okay, you have one error here. Somehow we have to detect the error. And that error can be detected by applying this translation of C2 to this operator. And that is nothing but C1, C2. You apply C1, C2 on this particular state. Okay. X2 on this will be translated to this. And now you apply C1, C2 on this particular state. Alpha 0, 1, 0 plus beta 1, 0, 1. You will end up getting minus of alpha 0, 1, 0 plus beta 1, 0, 1. So you get a negative sign because your error is X2. This is actually equivalent to X2 here. Okay. So you try to correct the errors that can be corrected, or that can be corrected using this redundant qubits, whatever that we have as redundant. Okay. Is that clear? Like, so is it fine? So the focus is these operators, Z1, Z2, Z2, Z3, and Z1, Z3 are identity. So what we normally do is we check whether this operator commutes or anti-commutes with the error, or we since we do not know error, we have an arbitrary state psi. This is, say, psi will be equal to alpha times 0, 0, 0 plus beta times 1, 1, 1, and you apply some arbitrary error e times psi. Now you do this measurement, you check whether C1, C2 times E psi will be equal to E times psi or minus E times psi. Okay, and there are techniques to compute this sign, to extract this sign. We will talk about that extraction later on. For now, we assume that this sign can be extracted. Okay, there are techniques called phase estimation algorithm. If you know that the exact algorithm is phase estimation algorithm. Okay, so you will be able to extract this sign here. Okay, using separate circuit or syndrome extraction circuits. Okay, so now the only thing is we are going to find this, and based on this sign we are going to detect whether there is an error or not. So what we will do, so we will apply Z1 Z2 times psi, and this I can call it as phi. So that is one, that is the received state. So we apply Z1 Z2 times psi. I will check whether it is plus phi or minus phi. Okay, one of these two. If it is plus phi, then fine, there is no error detected. If it is minus phi, there is some error detected. That is the idea here. Okay, and now, so the next thing is we have to so the first thing, whatever the summary is, we have to focus on ancilla qubits, especially the C operators on ancilla qubits. Okay, how the C on ancilla qubits is translated after the encoding. And in this case, we have C2, C3, C1, C3, and C1, C2, and identity. Okay, now we will focus on these operators. Now I went through this kind of encoding because I want to convince you that there are certain measurements which are not going to affect your information. So you are going to measure the information that corresponding to the ancilla qubits. Now you are not going to measure C1, C2, C3 because you are not going to measure C1 or C2 or C3 because this corresponds to logical information. So this affects your information. So if I take arbitrary state psi, valid quantum state, you apply C2, C3. Now this will be equal to remain psi. Okay, that's why these operators are called as stabilizers. So why these are stabilizers? So if I take a valid code, say alpha times 0, 0, 0 plus beta times 1, 1, 1, you apply these operators, say take C2, C3 and apply on it. This remains as alpha times 0, 0, 0 plus beta times 1, 1, 1. This remains in the same manner because if you go back and see the encoding circuit. So if you go back and see the encoding circuit, so this C2, C3 corresponds to the logical operation on the ancilla qubit. So even if I force your ancilla qubits, nothing is going to happen in your information. But then again, your ancilla qubits are initiated with 0 state and you are trying to focus on C operators. So C operators on 0 state is not going to do anything to your state. So whatever C operator, the equivalence of these C operators here are going to be translated here. Okay, so this gives us to another relation that if you have n qubits, so you have so suppose your code has n qubits. So suppose you have n qubits encoding k qubit of k logical qubits, which implies you will have n minus k redundancy. Okay, so in this case you have 3 redundant qubits and 1 logical qubit, and overall you have 3 qubits. So n equal to 3 and k equal to 1 and n minus k is 2. So usually if I wanted to have n comma k comma, we have one more parameter d. I will talk about d later. So if I wanted to have a n comma k comma d parameter, I wanted to have n minus k independent stabilizer operator. I wanted n minus k operators that corresponds to C in the ancilla. So I wanted to have n minus k operators corresponding to C2 to C n minus k. And the yeah, fine. And the next challenge is, how are you going to define this n minus k operators? And the definition is, you apply C on this qubit, apply C on this qubit, they are not going to affect each other. So C1 on C2, C1 on first qubit, this ancilla qubit, and C on this ancilla qubit, they are not going to affect with each other. So I wanted these operators to be commuting. So I wanted n minus k independent Pauli operators that are commuting. So if I can do that, then things are fine. Okay. So now for that I have to define, with this motivation, I wanted to define stabilizer codes. Okay. So earlier we started with some ancilla operators on ancilla qubits and so on. Now we force, so in this case, in this scenario, so we started with the operators here, and then we moved on to operators here in this regime. And now stabilizer codes are defined by using the operators in this regime, and we characterize these operators, and we are not, and we assume that there exists a circuit that can convert the ancilla C to this ancilla C, and there exists when these operators are commuting. So stabilizer codes, we define something called stabilizers. This is set of n qubit Pauli operators. Pauli operators mean made of I, X, Y, and C. Yeah. N qubit Pauli operators such that they commute. So what do you mean by commute? If I take an arbitrary operator S1 from S and S2 from S, I take two arbitrary operators from S1 and S2, then S1 times S2 should be equal to S2 times S1. So I wanted this property to be satisfied, and this is a property that I am operating on this qubit and operating on this qubit, they should be independent. And you are talking about Z operators, and Z1 and Z2, all these things, operators will commute with each other. So all these ancilla Zs will commute with each other, like all these will satisfy this condition. So I wanted my Pauli operators here also to be commuting, to make sure that I want a valid code state. I wanted a valid encoded state. Okay. So this is the first condition. And apart from that, I wanted another condition, which is minus identity should not be in stabilizer. Okay. And these two conditions will make sure that you have an appropriate encoding scheme for this code. And minus I does not belongs to S means, suppose minus I belongs to S, your I times I will be equal to, minus I times I will be equal to minus I. But when I define stabilizers, I wanted these operators for my code state, I wanted these operators in such a way that this minus I times I should be equal to psi. So for these two conditions to be satisfied, I wanted my minus I equal to psi, which is not possible in a valid quantum state. So I wanted my minus I not in S. So this additional condition that will be imposed. Okay. An example for one example is, for this is, you can have C1, C2, C3, C1, C3, and C2, C3, and identity. Identity and everything. So this particular set is the one example for this. And if I take any two operators, they commute with each other. And if I take, so that is like Z1, Z2 times Z1, Z3. If I take this is exactly equal to, since these two acts on same qubit, they are going to be affected. So Z1 and Z1, they are going to be commutative. So Z1 can come this side. So this can be pulled out in the front. And similarly, Z2 and Z3. So, sorry. So Z2, and here there is nothing on the second qubit. So here you have Z2 and here there is nothing on the second qubit. So that can also be commutative. So I can put Z1 separate and Z2 can come outside in this direction, and here you have Z3 and identity, so Z3 can come forward. So P1, P2, S1, S2 is equal to S2, S1. So you have commutative operators. Okay, and another interesting thing is we can represent using something called a symplectic form. Okay, so in this symplectic form, we are going to represent identity by 0, 0. That is, we are trying to give a binary representation for these operators. Okay, so we give zeros, we represent identity by 0, 0, x by 1, 0, okay, and c by 0, 1, and y by 1, 1. Okay, this is one nice representation that we try to use it. So if I try to use these codes, now if I have C1, C2, this can be represented by a tuple of 3 elements. Like, so you need 3 elements, and each component can be represented by 2 elements. So you have C1, C1 corresponds to 0, 1. So this can be corresponds to 0, 1, and C2 corresponds to 0, 1, C on second qubit, and there is nothing on third qubit identity, so it should be 0, 0. Okay, and this is not the symplectic form. In symplectic form, what we do is the first element of each qubit, the first point of each qubit, we will put at first. So the equivalent form is 0, 0, 0 in the first n qubits, and the second part 1, 1, 1 will go as the 1, 1, 0 will go as the second half of the n qubits. So here you will have n qubits, and here you will have n qubits. Okay, so you will have n qubits in the first half and n qubits in the second half. So you in the first half you represent all the existence, the presence of x in the first half. That is, whenever it is 1, you say that there is some x operator acting on that particular qubit, and similarly this component will represents the presence of c. If both are 1, it represents the presence of y. That is what we try to capture here. Okay, and now think about it. Suppose you have an error x1. Okay, now I wanted to see whether c1, c2 times x1 times your actual code state, your error. This is your actual code. This is your error, and this is your stabilizer. So suppose you are trying to measure the stabilizer on this particular received code word. So this is the received code word. Okay, in this particular received code word, if you are trying to measure the stabilizer, what happened to this is somehow I will push this to this side. So I will try to push this to this side. So what happens is, so C1 times C2 into X1. Now this will be equal to, so in the first qubit, if you notice, you have C1 and X1 acting together. Okay, so now if so earlier when we talk about the commutative operations of Pauli operators, we talked about this property, that is x is equal to minus cx. So we talked about this property. So we apply that property here. Now c acting on first qubit, x acting on first qubit. I wanted to pull x1 first, so a negative sign will come up. Okay, and the remaining operator can move that side, so it becomes c1, C2. Second qubit, there is nothing, so there is no issues in getting a negative operator from the second one. Okay, so whenever there is an x and c, there is a negative sign that comes out. Okay, and now suppose you have x1, x2. Now this c1, c2 will not capture this particular error x1, x2, because when I try to pull x1 in the front, so you have c1, so you will have a minus sign, and when I try to pull x2 in the front, so since this is c2 and this is x2, there will be a negative sign. Okay, there's one more. These two gets cancelled each other. Okay, if you have two negative signs, they get cancelled each other. So now this can be represented in the math form too. So now you have this c1, c2 represented by 0, 0, 0 and 1, 1, 0. Okay, and similarly this one as a symplectic form 1, 1, 0 and 0, 0, 0. So you have x on 1, x on 2, and there is nothing corresponding to c on any of these qubits, or x on nothing on the third qubit. Okay, so this a binary representation of this is this one. So we do something called a symplectic inner product. So what we do, so we take this vector 0, 0, 0, 1, 1, 1, and we multiply with a matrix which is identity 0, 0, identity, identity 0. This matrix is called a symplectic matrix. We normally represent by like this, and it's multiplied by this vector, the transpose of this. So you have 1, 1, 0, 0, 0, 0. Though the necessity of this symplectic matrix is it pulls the x part to the z part and z part to the x part. And if you notice this will be exactly equal to 0 in this case, if you try to calculate this, because they commute. So whenever this two Pauli operators commute, their corresponding matrices under a symplectic inner product, that will give you 0, right? And similarly, if I take, so this corresponds to x1, x2, so this corresponds to x1, x2, and this c1, c2, and this corresponds to x1, x2. And similarly, if you think about this operator 0, 0, 0, 1, 1, 0, right? 1, 1, 0, and 0 identity, identity 0, times 1, 0, 0, 0, 0, and this corresponds to x1. Okay, so you have 6 elements, right? 0, 0, 1 more 0. And if you see, this will be exactly equal to 1. Okay? So whenever the point is, whenever the Pauli operators anti-commute, the symplectic form will be, so the product, the inner product of this inner product, this we call it a symplectic inner product. The symplectic inner product of their symplectic forms will give you 1 when they anti-commute, and that will give you 0 when they commute. And that is the key observation here. Okay. So now this will give you the complete connection to the classical codes. So now you have two Pauli, you have a Pauli operators, stabilizers. Okay. So stabilizers are a particular group of Pauli operators. In this case, you have C1, C2, and C2, C3, C1, C3, and identity. This is the stabilizers. And now this can be represented by a symplectic form. The C1, C2 can be represented by a symplectic form 0, 0, 0, 1, 1, 0. And C2, C3 can be represented by a symplectic form 0, 0, 0, 0, 1, 1, 0, 1. And C1, C3 can be represented by a symplectic form 0, 0, 0, and 0, 1, 1. And the remaining is identity, that is all zeros. Okay, so you have 4 vectors. On seeing these 4 vectors, you can see that there is a connection here. Like, so they are, it forms a vector space. If you take 2 elements and take the sum, that third, you get another element. So this one can have a basis element or a generating set. So we take only the generating set and put it in a matrix form, that is 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1. So you put only the generating set. We don't care about the remaining set. Why? Because if I take this vector, let us call it as H1, H2, and if I take H1 times your symplectic product and some E transpose, which is equal to 0, that is, they say that it is not an error, or maybe we call it as some B naught. It can be B naught, can be 0 or 1. Okay, and similarly you have H2 inner product with the same error E transpose, which is equal to B. We call it as we can call it as B1, and this one can call it as B2, which can be 0 or 1. Now we can see that if you take H1 plus H2 and you try to take the inner product E transpose, this is equal to B1 plus B2. So when I add here, the resultant also is summed up. So instead of focusing on all these operators, you focus only on the generators. So we focus only on these particular matrices, this particular generating the matrix form corresponding to these particular operators. So this one we call it as a parity check matrix H. Okay. So how will you detect an error? So you have a parity check matrix H. You have the symplectic form, that is lambda. This lambda equal to 0, identity, identity 0, times you have some R transpose, or this one is called E transpose, and you check whether this is 0 or not. This one we call it as syndrome. Okay, syndrome. So is that clear? Is this equation clear? This gives you the complete connection between the classical error correction code and a quantum error correction code. So that is H times H corresponds to the parity check check matrix. Okay, so though this is a quantum error correcting code, but by constructing certain classical error correction codes, we can construct quantum error correcting codes. That is the idea here. Okay, so is that clear, or do you have any questions? So far the key point is quantum error correction code can be represented, or this one is more specifically something called a stabilizer code. Okay, not all quantum error correction codes can be represented by a parity check matrix H of size n minus k cross 2n. So it should have a length 2n vectors, and the size, the row size should be n minus k. Okay, and error detection will be you check H times lambda E transpose whether this is 0 or non-zero. 0 means then there is an error detected. Non-zero means no error detected. Oh, sorry. 0 means no error detected. Non-zero means error detected. This is the takeaway here. And then how are we going to do this? That we can do it using a quantum circuit. To be specific, we are not going to find out. We do not know E actually. We don't know what the error is. So computing this is not that easier. Like it doesn't seems to be easier from this perspective. But from this perspective, that is S times psi, it should be equal to psi. When there is an error, my S times E times psi should be equal to plus or minus E times psi. And there's a technique to compute this phase. This is called phase estimation. Okay, and if the symplectic form corresponding to S and symplectic form corresponding to E, I call it as H lambda E transpose. If this is equal to 0, then this will be plus psi, and if this is equal to 1, then this will be minus E times psi. So that is the idea. So we compute this using a quantum circuit. By using phase estimation algorithm, we try to compute whether this is plus 1 or minus 1. But then in the math form, we can put it using this equation. That is, my syndrome S is equal to H lambda E transpose. So this will be my the overall error correction problem in the quantum error correction in one word. Okay, but then there are other restrictions too. Okay, we will come into those restrictions. And so the decoding problem here is given S, compute E. So this will be my decoding problem in this case. Okay, given S, you are supposed to compute E. And again, all these techniques that we use in classical error correction codes, with some small adjustments, we can apply for quantum error correction codes. That is the recent research on how to convert the classical belief propagation decoders, or the decoders that are used for classical error correction codes. We try to convert that to quantum error correction codes. Okay. And one more restriction that I want to talk about is this restriction, that is stabilizers commute with itself. Suppose you take a state psi be a valid code state, and you take defined by stabilizer S, and you take any operator S from S and apply on the state psi. Si should be equal to psi. This one we have seen earlier, right? Now suppose your error E equal to S. If your E is equal to S, then my E times S, so this is E times psi will be equal to psi if E equal to S. Now if I take any stabilizer, take S1 from S, S1 need not be equal. S1 can be equal to S or need not be equal to S. Now if I apply S here, S times S1 times E times psi should be equal to S1 times psi, and now S1 is again a stabilizer, so this should be equal to psi, and this is again can be written as E times psi. So your F1 times E should give you +1 eigenstate always. It should not give you -1 when your error is a stabilizer, right? So which means when my error belongs to the row space of H, that is any of the stabilizers, that is the error belongs to stabilizers. This is equivalent to saying the error belongs to row space of H. Whenever my error is in this category, then my H lambda E transpose should be equal to 0 because they commute. All these stabilizers should commute. So because S1 times E should be same as E times S1. So you should end up getting the same. Okay. And to make sure this condition, we add another condition, that is H times lambda times H transpose should be equal to 0. We do this condition. This is an additional condition that is imposed. So we can have any classical parity check codes of H length 2n, but then we have additional constraints, and this is the additional constraint that we are supposed to impose to define an arbitrary error correction in quantum state. Okay, right? And this particular property can be extended further. Suppose I have H, I group H in a nice way, that is I have Hx 0 0 Hz. So suppose I construct, if my H is like this, then this condition H times lambda H transpose equal to 0 will tell you something like Hx transpose Hz should be equal to 0. Oh, sorry. Hx Hz transpose should be equal to 0. And so now this is another interesting property. If my H is restricted like this, then I wanted to enforce this condition, Hx times Hz transpose equal to 0. And whenever this condition is imposed, we call such codes as CSS codes. So these are defined by Calderbank, Shore, and Steen. So this is the abbreviation of their names, first letter of their names. Okay. So if your H is of this form, this is the extra condition that we have to impose. And how this condition can be translated, if you try to look at this, now you can see two classical codes lying there, here, concatenated with each other. Okay, so this Hx corresponds to a parity check matrix of a code space C1, and similarly Hz is a parity check matrix of another code C2. Okay, and then if you focus on this condition will tell us that if you can observe this Hx, that is, since this is parity check matrix, Hz can be represented by C2 transpose, C2 orthogonal, that is null space of like the orthogonal space of the code space. Okay, so these are generated by the space of Hx, row space of Hx. So C2 transpose is row space of Hx. This C2 transpose, C2 perp, the orthogonal vector space of C2 is generated by row space of Hz, and this C2 perp should be a subspace of my C1, like, right? C2 perp should be a subspace of C1. So these are called, like, so I wanted two code words C1 and C2 such that my C2 perp should be a subspace of C1. In that case, I can construct two parity check matrices Hx and Hc for code words C1 and C2. These are classical code words. Okay, so these are classical code words. If this condition is enforced, then we can construct a quantum code word with a parity check matrix corresponding to Hx 0 0 Hz. This is the final takeaway. Like, if you have two classical code words with parity check matrix Hx and Hz and satisfies this condition, then we can construct a quantum error correcting. Okay, and this Hx and Hz should be n bit. So you have n and you have n here. Okay, is that fine? And these codes are CSS codes, and these are the codes that are that are studied widely because of its simplicity. And there are statements that states that if you have a non-CSS code which cannot be written in this form, we can always convert it into a CSS code. If you have a non-CSS code which cannot be written of this, if the parity check matrix cannot be written of this form, you can always convert it to some other code for which the parity check matrix can be written of this form. So people mostly focus on the quantum error correcting codes for which the parity check matrix can be written of this form, and these are called CSS codes. Okay. And now we can focus on some examples. Okay. So the first, the simplest example that I will talk about is, so we talked about a Hamming code which have a parity check matrix of 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, oh sorry, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So this will be your height checks. And now if I take my height set equal to height checks, this gives you an interesting code. Again, if you solve it, you will end up getting this height checks times height checks times height set transpose will be equal to 0. So you will, if you try to solve this, you will end up getting this, and this is exactly your the Hamming code. This one in quantum sense it is called a Steen's code, Steen's 7-qubit code. Okay, and or in other words, this is also named as a color code of distance 3. So if you of distance 3. Okay. So if you go back into literature and see the word color codes, and this is one of the basic example for color code. We will if we have time, we will try to discuss color codes. Yeah. And now, most of the time, we don't characterize how the code words look like. So if you wanted to see how the code words look like, so in this case, it will look like something like 1 by size of C, summation over all code words in C, your C, where your C is nothing but the code words of Hamming code, the classical Hamming code in this case. Okay. So the code words of classical Hamming code, you take it and you sum up over all those things. So you get a valid quantum state. So that this is one example, like one particular state here. And now you can apply more and more logical operators, and you can try to generate more and more things. That is, like you can generate a psi1, which is 1 by size of C, summation over C in C, and apply a x bar times C, where my x bar equal to x1, x2 to x7. Okay. And what is this x1 to a? Yeah. Yes. Okay. So what is this x bar? X bar is nothing but, earlier when we talk about 3-qubit repetition code, we talked about this. So we talked about 2 ancilla qubits, and we talked about 1 information qubit. Any operation on this information qubit will affect your information itself. So we try to see how the operations on information qubit will be translated in this region. And the X operator on this information qubit, in the case of 7-qubit code, that will be translated into this X bar, X1, X2 to X7. So I try to put up a logical, I try to change the logical information of my, so normally this one can be encoded as logical 0, and this one can be encoded as logical 1, that applying some logical X on it, or something like this. Okay. And similarly, you can try to get logical -1, 2, and this can be applied by some side 2. This is 1 by C, summation over C in C, and you apply some C bar times X bar times C, where my C bar equal to C1, C2, C3. Okay, sorry, it's not C1, C2, C1, C2, C3, and identity under remaining qubits. This is one logical C operator. So or you can talk about this too: C1, C2, C3, C4, C5, and C6 and C7. This is also one logical C operator. So you apply this, you end up getting other logical informations. Okay, so with this introduction on CSS code, so far I tried to introduce CSS codes. Okay, so if you have any questions, you can clarify it. Like, so with the on the introduction on the CSS codes. So no questions. Okay. So right, no questions, right? So CSS codes, the idea is you have a parity check matrix, I check 0, 0, I set. Now we see another common example for CSS codes, which are commonly called as surface codes. Okay, so this belongs to a class of codes called topological codes. So these are this is one of the earliest quantum error correction codes that has been studied in the literature. Like once, so all the other codes that came after this. Okay, and how do we define surface codes? Now the goal is you have to identify this parity check matrix H, which have this component H checks 0, 0, and H set, and such that my H x times H set transpose should be equal to 0. I wanted these conditions to be enforced. So what we do, we take some graph. Okay, say you draw a graph. Okay, and so in this talk, I will try to focus on something called surface codes on planar. We will talk about something called toric codes. Okay, so you take arbitrary graph. Okay, so maybe I will draw it a little bigger so that so this can be arbitrary. You need not have to be you need not draw the square lattice square graph every time, but and this is but square graph is more commonly used because of its symmetry. Okay, so what symmetry means, it can correct both x error and c error on the in the same fashion. Like, so the same kind of algorithm can be used for correcting x error, and the same kind of algorithm can be used for correcting c errors with a slight tweak. Okay, and so with that sense, this surface codes are useful, like the toric codes are useful. And how do we define toric codes? We draw this graph, like, right? We draw an arbitrary graph. So in this case, I have drawn 1, 2, 3, 4. Oh, sorry. Sorry. Okay. So you draw an arbitrary graph and you draw it on a torus. So how can we visualize torus? It is this vada shaped. Like, so if you know vada, it's a vada shaped, or this is like a donut shaped. And so how can we visualize in a plane? So you draw this graph and you attach this qubit and this qubit. So for example, if I number these qubits, this qubit can be numbered 1, 2, 3, 4, 5, 6, and when it comes to this qubit is same as this qubit. So this is same as 4th qubit. Okay, and similarly, so 1, 2, 3, 4, 5, 6, and this will be 7th qubit, 8 and 9 qubit, 10, 11, 12. When I number this qubit, again this will be same as the 10th qubit. Okay, and this will be 13, 14, 15, 16, 17, 18, and this one will be 16th qubit again. Okay, and these qubits, it's kind of a donut structure. First, by attaching this 4 and 4, 10 and 10, and 16 and 16, I made a cylinder structure. And now attaching on the top and bottom, that is 1 and this one also will be 1, and this 2 and 2, and this 3 and 3. So I got a cylinder structure. Now I attach the both ends of the cylinder, so I get a torus structure. Okay, so this one is called the surface codes. Okay, so what I do is I place my qubits on all these edges. So all qubits on edges of the graph. I place my qubits on edges, and now I have to define x check and c check. So what I will do is I will place all my x check on all the vertices. So how am I going to place an X check? So I take say high checks I wanted to define. Let me try to take this node. So if I take this vertex, this has qubit 1 incident on it. So I place 1 in the column corresponding to qubit 1, and the next edge incident on it is qubit 4. So I will put 0 on qubit 2 and 3, and qubit 4 I will put 1 because this is incident on it. Now if I see qubit 3, that is also incident on the same vertex because these two vertex are same because of our cylindrical attachment. So qubit 3 is also incident on this vertex. So I normally put 1 on qubit 3, okay, and the other qubit that is incident on it is qubit 16, right? It's qubit 16. So I have 1 0 1 1 and 4 zeros, again 4 zeros, again 3 zeros and 1. So I put the 16th position, I place 1. So thus I will try to construct a the high checks matrix. Okay, and I have 2 more qubits which are 0 0. So I have high checks, and now that is the first row of high checks, and now I wanted the second row of high checks, so I will go for the second vertex. So I go to this vertex. Now there are 4 edges incident on it, that is qubit number 1, qubit number 2, qubit number 5 and qubit number 17. So I will place 1 on qubit number 1, qubit number 2, 3 4 remains 0, qubit number 5, and after that qubit number 17 is 1, and all the other qubits are zeros. Okay, and similarly I can construct, so for all the other nodes I can construct the corresponding row elements of high checks. Okay, and similarly once I constructed high checks, now I have to construct high set. Okay, and so we will talk more on high checks, but let us define high set too. Now high set, they are identified by the phases. Say for example this phase. So this phase, in this phase there are 4 qubits, that is qubit number 1, 5, 4 and 7 are incident on it. So I apply 1 on qubit number 1, 2, 3, 0 and 4, 1, 5, 1, 6, 0 and 7, 1 and the remaining 0. Okay, and next I go for this phase, and qubit number 2, 1 and 3, 4, 5 and 6, 1 and 8 is 1 and all the other qubits are 0. Like, so you don't act on it. So thus you construct high checks and high set. Okay, so this high checks and high set together will define your surface codes, like toric codes. And if you think about it, the advantage of this toric code, this surface code is, if I want to measure the syndromes, now if I want to measure the syndrome, like what I can do is I can construct physically construct a plane or a 2D surface where I can place my qubits along similar to this graph. I place it physically that looks like this graph. And now if I wanted to measure a stabilizer, now if I wanted to this stabilizer, now I can create circuits with this stabilize this qubit, this qubit, this qubit and this qubit. Since these 4 checks, these 4 are the qubits that needs to be checked for this parity check, I will focus on these 4 qubits alone. So all these qubits are placed next to each other. So they don't propagate noise. Like, so you don't have to. So the quantum computers these days are highly noisy. And now if I want to interact with the qubit 2 with the qubit 14, then you have to connect wires between qubit 8 and 2 and 14 and or 8 and you have to pass either qubit 8. Oh, sorry. In this case, 2 and 14 are connected directly, but in a larger graph, if I go for a bigger graph, okay. So if I go for a bigger graph, if I wanted to measure the stabilizer here, I have these 4 qubits interacting. But if I have an interaction between this qubit and something this qubit, it should always pass another qubit here. The connection should pass another qubits, so which can add more and more noise to your system. So these surface codes are a boon for early quantum computers where your connections can be local. So in those cases, we've enforced this local connection here by using this kind of parity checks, which are local. So this is like you have locality here, some sense of locality here. You measure the stabilizers are measured using local qubits. Here locality meaning syndromes measured using local stabilizers. Okay, so that is the idea here. And so that these are so most of this practical error correction codes in the early stage of quantum computers, they focus on this surface codes, implementing the surface codes there because of this property. Okay, and but the challenge in this surface codes are, so if you think about the number of logical information, they are always two here in this case, in the Tori code, in Tori code case. In a planar graph, so there is another class of surface codes that people usually tend to implement is something called as planar surface codes, where the number of logical information is 1 for planar surface code. Okay, so this is highly challenging. Like, so if anyone have idea on coding theory, so this has n comma d, k comma d parameter, where n can be arbitrary n, but k is always 2 and d can be proportionate to n. Like, so in this case, d is usually proportional to it is proportionate to square root of n in surface code case. So if someone knows yeah, sorry. Yeah, the biggest challenge here is the number of encoded qubits k is constant every time, and this k by n is an important parameter in classical error correction code, which we call it as rate of the code. Okay, and as rate is higher, the code is better. Like, we wanted the higher the rate, and we have another parameter, we call this as d by n, and we wanted d by n also higher, which is always not possible. There are constraints, but we tend to have this k by n at least a constant. As I increase n, my k should be increased proportionately. But in this case, if you see here, whatever may be n, the k is 2. Okay, that is one biggest challenge in case of surface codes, because as you sorry, so as you increase n, so if I use limit n tends to infinite, 2 by n, this goes to 0. So these are called zero rate codes. So you cannot encode more than two qubits there. Okay, so to overcome this challenge, people go for another class of codes called quantum LDPC codes. So I will just introduce quantum LDPC codes, and then I will talk about something called as trellis decoder, which is one of my work earlier. Trellis decoder, I hope some of you may be knowing trellis, something called trellis diagram and how to work on trellis diagrams. And so these
Arun,
are, yeah.
So we want to stop at 7:30. Is this a good time to stop, or you want to take some more time and then resume at 8 o'clock? How is it?
Yeah, I will stop here. So I just wanted to tell you what are the other topics in error correction codes that I am planning to talk in the second session. Okay, so I will introduce this. I will talk about this QLDPC codes where they are beneficial. I will just introduce and I will leave it. Like, so I won't talk in detail because there are other. So I heard that there are other sessions who are working on this quantum LDPC codes. They are planning to talk about this quantum LDPC codes, and I will talk about a class of decoders called trellis decoders, which are derived from our classical error correction codes. Okay. So, and then motivate that we can always convert a classical error correction decoder into a quantum error correction decoder. And after that, if time permits, I will talk about this introduce quantum algorithms, if time permits. Like, so earlier I planned for one session on error correction codes and one on algorithms, but now since we are exceeding more time, so I want to focus more on this error correction code. So we will talk about this first, and if time permits, we will introduce quantum algorithms here. So if you have any questions, you can clarify that. Otherwise, we will stop here.
So in quantum, do you have error detection also, like what you have in classical algorithms? Do you have error detection also in quantum?
Yeah, we can do the error detection. Like, so it is the same, similar to what we do in classical error detection. So the syndromes will help us in error detection, And when the syndrome has more capability to separate your code, so classically we have this, right? So we have so we encode like information like this, and if you have the capacity, if your noise is under this level, within the limit of this radius, then we can use the same error correction code as error correction code. But if your noise is going exceeding this limit, so if, say for example, if your noise is exceeding this limit, it moves here and here, and then in those cases we will try to use error correction code as an error detection code too, using the syndromes. If the syndrome is non-zero, implies error detected.
Okay, thank you. So I
Yeah,
think we
the
will
same
meet
way
again.
we do in classical.
Yeah, we will meet again at 8 p.m.
Okay.
Yeah. So for participants, I have shared in the chat box the attendance sheet and the feedback for yesterday and today. You can give it there. Attendance sheet I will download after today's session, the second session. Feedback you can do anytime, either today or tomorrow, whenever you are free, you can do. Okay. Attendance you do by today itself. Thank you. We'll meet at 8 o'clock.
Okay, thanks.
Yeah. So let's welcome Dr. Arun for the second session of the day. Dr. Arun, you can take over. Yeah. Thank you. Arun, I guess you have to unmute yourself. Is Arun audible to others? Can someone comment or chat? I am not able to hear him. What about others?
Audible, sir.
We can able to hear you, sir.
Audible, sir.
Some are saying not audible. No.
Sir, for
Dr.
me, it's
Arun
audible.
audible to you. Sudarshan is audible.
Audible.
Is Dr. Arun audible?
Is not audible.
Arun, I think you are on mute. Arun, you are not audible. Maybe can you just log out once again and log in and try?
Sir,
Yeah, let's wait for some time for Dr. Arun to rejoin.
Am I audible? Hello?
Yes, you are
Yes,
audible,
sir.
Dr. Arun.
Audible,
Arun, you
sir.
are audible. Yeah.
Oh, okay, fine. So I couldn't turn on my camera. I don't know what is and this is connected by properly. So I couldn't turn on my video. Okay. So I will just
That is
maybe
okay.
there.
You see if you can share your screen or something. Yeah.
Yeah, I will share my screen. Yeah. Is it fine? Is it fine now?
Yes, sir.
Yeah,
Yes, sir.
your
We
entire
can see.
screen is visible. Yeah. Yeah, now
Okay.
the slide is visible. Yeah.
Okay, fine. Okay, just to summarize what we have discussed so far. So we talked about the code words, like, so when we define a quantum error correction code, so normally we define them using something called Pauli operators, so which are formed by IX Y and C operators. These are single qubit operators. This can act on multiple qubits. I on first, X on second, Y on third, and so on. Like it can act on multiple qubits. And it is formed by a group called stabilizer group. It is set of n qubit Pauli operators. Okay, such that you take S1 and S2 on S. So S1 times S2 will be equal to S2 times S1. And minus identity is not in my stabilizer group. And now if I want to define my code words, my quantum code words, all possible valid code words are defined by set of all states such that my S times psi should be equal to psi for all, okay, for all valid stabilizers. Okay, so if I apply all stabilizers, it should commute. Okay, so the simple example that we have seen is repetition, where you have the stabilizer group defined by Z1, Z2, Z2, Z3, Z1, Z3, and identity. So, and the code words will be all possible values of alpha and beta that satisfies alpha times 0, 0, 0 plus beta times 1, 1, 1 for alpha and beta belongs to complex numbers. Okay, so this is how we define the code word. But in most of the time when we talk about code words, we don't see this in quantum. So this is usually seen in classical. Classically, we focus on code words. But when we talk about quantum, we talk about stabilizers. And we saw something called a symplectic form, for which my X is mapped as 1, 0, C is mapped as 0, 1, identity is mapped as 0, 0, and Y is mapped as 1, 1. So I do a mapping like this, from which my Z1, Z2 will be translated as 0, 0, 0, and the first one is Z1, so it is 0, 1. So Z corresponds to 0, 1, so I have 0, 1. Second one is Z2, so 0, 1. And third one is identity, so 0, 0. So you have a matrix like this, and in the same way. And then we talk about two Pauli operators, P1 with the symplectic form, say H1, and P2 with symplectic form H2. And now P1, P2 is equal to P2, P1 when H1 lambda H2 transpose equal to 0, and P1, P2 equal to minus P2, P1 when H1 lambda H2 transpose equal to 1. So these are the conditions that we have seen so far. Like so under these conditions, if you have an arbitrary error E acting on your code state psi, and now what we do is we do this measurement, Pauli measurement P, say for example P1 times E psi, and we will check whether this is plus time E psi or minus E psi. Whether we compute this, the term that comes out of it, whether it is plus or minus. Okay, to guess this, what we do is we check whether P1 times E equal to plus or minus E times P1. If it is plus E times P1, then we say that the error is not detected by this stabilizer. But if it is minus E times P1, we say the error is detected by the stabilizer, which means the error detection, this negative sign, is captured by syndrome, which can be written as H1 times lambda times E transpose, where E corresponds to the symplectic form of this capital error, the error E. Okay, so this one captures this S will be equal to, so I call it as S1. S1 is equal to 0 when you have a plus sign, and equal to 1 when negative sign that comes out. Okay, so negative sign is the one that corresponds to the syndrome. So for more general case, we have something called parity check matrix, and we compute syndrome S equal to H lambda E transpose. And this syndrome is computed using a quantum circuit, and we find out whether plus comes out or minus comes out. I will talk about the quantum circuit that computes this syndrome in the end of this talk. And whatever we know is yes. So our decoding problem will be given yes, find E transpose, find E. Okay, and this is exactly similar to our classical error correction problem, where my syndrome equal to H times R, and our goal is to find given yes, find R. So the goal is usually given as find R or find, and this will be exactly equal to H times E. So our goal will be given as find E. Okay, so this will be exactly equal to H times E transpose or H times R transpose and so on. Okay, so classically we do this. Given yes, we find E transpose. In quantum sense, similarly we do. Given yes, we try to find E transpose. That is what the most of the quantum error correction course, the error correction procedure that we work on. Okay, and now our goal is given. There are two goals. One is code construction goal, like code construction. This is focused on how are you going to construct H, and this H will have a bigger form of two sizes, and then we introduce something called CSS codes where this has a specific form of HX0 and 0 and HZ. This one is called CSS codes. So we focus on CSS codes where HX times HZ transpose is equal to 0. So we focus on these codes. So our code construction is to construct H such that my HX times HZ transpose equal to 0. And there is another problem, decoding. In decoding problem, the problem is given the syndrome S, which is equal to H lambda E transpose, comma H, find E. Again, there are words like optimal and so on, like we go for minimum weight or the maximum likelihood E and so on. So all those terminologies are similar to the terminologies that we use in classical error correction codes. Okay, but the goal is given yes, find E. Okay, so for now I thought of having one base idea on how people construct codes these days, like more general codes called quantum LDPC codes, and one example for a decoding algorithm which we worked on in the past. Okay, so that is the next that is what I planned for this session. Okay, so when we talk about, first I want to talk about how people construct quantum LDPC codes. Yeah, more detail of this quantum LDPC codes will be given by different speakers in the forthcoming sessions. Today I will just introduce how people these days construct quantum LDPC codes. Okay, so one of the most famous construction, which we call it as product construction. Okay, so the idea is we take two objects, say let us call it as A1 and A2, A3, and we try to find a map from A1 to A2 and A2 to the A3. That let me call this map as delta 1 and let me call this map as delta 2. So the idea is we take three objects A1, A2, A3 and try to find a map from A1 to A2 and A2 to A3, delta 1 and delta 2, such that I pick an arbitrary element A in A1. Now I apply delta 1 on A. I get some element from A2. Then I apply delta 2 on this thing that I get from A2, and this should be 0. This condition is helpful. And now when my delta 1 and delta 2 are linear operators, that can be represented by a matrix operation, which means delta 2 times delta 1 acting on any vector A should be equal to 0 vector. Or in other words, my delta 2 times delta 1 should be equal to 0. Delta 2 and delta 1 are two matrices when we talk about linear operators. So delta 2 comma delta 1 are matrices and with the multiplication compatibility. So when we talk about compatibility, so when it say that delta 2 times delta 1, the matrix dimension should be in such a way that there exists delta 2 times delta 1. That's the only constraint that we try to keep it now for now. Okay, and what does it mean? I can always define my Hx equal to delta 2 and H is a transpose equal to delta 1. So which means earlier I wanted this Hx, H is a transpose equal to 0. Now Hx, H is a transpose here will be same as delta 2 times delta 1 transpose, delta 2 times delta 1, okay, which should be equal to 0. This implies my Hz should be equal to delta 1 transpose. Okay, so can find these two matrices nicely. So the goal is, if I can construct some object like this chain complex. So we call this as chain complex. The word, the terminology is chain complex. Okay. So if you have three objects such that you have this is 0, which if I can construct a linear chain complex like this, then I can always have a quantum error correction code that comes out of it, where I can place my qubits on A2 and one type of check on A1, one type of check on A2. So as an example, if you see the surface codes. So if you go for this, you take a symbol node, and now here my objects A1 are faces, okay, and A2 are edges, and A3 are vertices, and delta 2 are boundary maps. Delta 2 and delta 1. So what does it mean by boundary map? I take a face, this face. Now I take the boundary of this face, that is delta 2. So delta 2 means I take the boundary of this face. So I end up getting this edge, this edge, this edge, and this edge. So I get 4 edges as the outcome of, so I get non-zero terms in these 4 edges, and I get 0 in the remaining, because this is the boundary operation. You take the boundary of this face, and now again you take the boundary of the next. In that case, I have to go for the vertices, and if I take the boundary of this edge, I will end up getting this and this, and boundary of this, again it will be this. So these two gets cancelled out. So 1 plus 1 is 0 in terms of binary addition. So this will be nullified. So I won't get a boundary here. And if I try to see here again, so you end up getting 1 from this and 1 from this, they get cancelled out. And similarly, 1 from this, and cancels out. 1 from this and 1 from this, they get cancelled out. So overall, you will not get a boundary. So this can form a nice chain complex from faces to edges to vertices. And thus, your HX and HZ can be constructed as the corresponding boundary maps. Okay. So this is a more general view of construction. Only thing is, we have to identify this A1 and A2. So how people, one simple way of identifying this A1 and A2 is using something called as tensor products. Okay, so maybe I will not go into the details, but for one example, at least I will try to give you. So you take a classical error correction code. So it is like H, right? You have a parity check matrix which corresponds to classical error correction code. Okay. Now, what does it mean? What does it do in H? So it takes all your elements from F to N. So that is your H times, if I take H times X, since H is N minus K times N, your X should be N times 1. Okay. So you take all vectors of length 2 and multiply by H. You get some vectors of length K, sorry, N minus K. So because of this, so you multiply by H and you get vectors of N minus K. And this object, you can call it as some class, since it is classical code, we can use the word C1. And this object, we can call it as some C2. Okay. And now this is a simple chain from C1 to C2. Now we normally generalize this chain by some object, like we call it as tensor product. That is, you construct C1 tensor C1 and you try to find, sorry. So you try to find a boundary map on the second object, that is C1 alone. You end up getting C1 tensor C2. So this is identity on the first object and H on the second object. Okay, and then you apply H on the first object and identity on the second object. So you will end up getting C2 tensor C1. So H on the first object and identity on the second object. Now you take this, you apply a map which is H tensor I, which is H acting on the first object, because H acts on C1. So things are fine. So H acts on C1 and I acts on C2. So this one becomes C2 tensor C2. Here also, if you apply I tensor H, H acts on C1 and I acts on C2. So this becomes C2 tensor C2. So you construct something bigger like this, and these two, this can be marked as sum A1, and these two together can be marked as sum A2. This operator together can be marked as sum delta 1, and these two operators together can be marked as sum delta 2, and this particular operator can be marked as, this particular object can be marked as A3. So thus we can construct a chain complex where we get sum delta 1 and delta 2 accordingly. Okay, this will lead to a quantum error correction codes, and by adjusting this the value of H and so on, we can construct better codes. So that is the one of the most recent or common way of constructing error correction codes in quantum sense. So that is the recent way. Okay, and that's what I wanted to say. If anyone interested to go into the literature, you can see there are a lot of literatures related to tensor product based construction. Okay. So any questions? So if you have any questions, yeah, please go ahead with the open mic. So I may not be like maybe chat or something. Okay. So okay.
So just a question, like quantum LDPC, do you have quantum polar codes also?
Yeah, there are quantum versions of polar codes also.
Okay.
Like for now, I do not know about quantum polar codes, but there are literatures talking about quantum polar codes too.
So in another question, so generally in the coding, in the classical coding theory, people are trying to use machine learning these days. So is the same thing being tried in the quantum codes field also, using some quantum machine learning and all those things?
Very recently, I saw a paper where they construct quantum error correcting codes based on machine learning. But earlier, before that, there are no successful code construction based on machine learning. But very recently, like it's just 1 week back or something, I saw that in my list, like in my follow list.
Okay, thank you.
So I believe that may give another fruitful direction from the merging of this quantum error correction codes and the machine learning that people do in classical codes. Okay. So the next thing I wanted to talk about is, can we port the techniques that we have in classical error correction code into quantum error correction code? From that sense, I will talk about one particular decoder called as trellis decoder. Okay. So there are other decoders. People work on belief propagation. This is more famous decoder, which has different names: belief propagation or message passing. So these kind of names you can search through. There are, so you can come across so many literatures. These are advantages because the decoding complexity is less. Trellis decoder, for now, it is not much attractive for large scale quantum error correction codes because the complexity of this decoder is still exponential, but it is far better. That is the catch here. But then this belief propagation or message passing decoders, their decoding complexity is much lesser compared to trellis decoders, which is polynomial in time. So they are more studied in the recent literatures. Okay, so I will talk about trellis decoder here. Okay, so now so this trellis decoder originates from the class of trellis decoders for classical linear block codes. So usually we use trellis decoders for convolution codes, right? That is where we use. So whenever we talk about trellis, we need a state. Like we usually have a current state and next state. So we have some connection from current state to next state, and then the same pattern should repeat, kind of thing. So you have current state, next state, current state, next state, and so on. So you have current state, next state, and current state, next state, and they somehow merge at some point. And then we want to find the optimal path from. Usually, the goal for trellis algorithms will be find the optimal path from one time instant t1 or initial state to some other final state. Yeah, so that will be the end goal. And in this case, in this trellis decoder, what we normally do is we take the stabilizer. Okay, say let us start with the example that we know. Like the example that we know is the repetition code. That's what we were talking about. that is C1 C2 times I, and C1 C3 and C2 C3 and identity. This is the stabilizer that used to construct the repetition. So now what we do is we construct something called syndrome trellis. And this syndrome trellis is like I wanted to draw a layer that corresponds. So for example, in this case, the number of qubits is 3, which means I need 4 layers of nodes. So for first layer, I should usually have this as all zeros. So I will have this first layer zeros, and second layer I may have some number of nodes. In this case, there are 2 non-zero syndromes. So we usually have 2 states, like 2 states. And second state, we may have something like this. And third state, like, first, 0, first, second, and third. And the last state, we will have 1 node. First and last state, we will have 1 node. And now the connection is, now you have C1, C2 Pauli operator. So take C1, like, so as a stabilizer, like you have C1, C2 as a stabilizer. Take C1. So apply C1 alone on the first one. And you check what is the syndrome that comes out of it. If the error is C1, what will be the syndrome? So there are two independent generators here. So one is C1, C2, and another you can take C1, C3. So these two can be independent generators, where these two helps us to generate the entire code. Now, if you have C1, then the resultant syndrome will be 0, 0. So you don't have any new syndrome. Okay, and the other single qubit Pauli operator can be X1. And now if you apply X1, you will end up getting a syndrome of 1, 1. So whenever you have X1, you will have 1, 1. So that is the first qubit state. Okay. And similarly from here, again you apply C1, C2. So this is first qubit, and this is second qubit, and this is third qubit. So the second qubit is, you can consider C2, and C2 will be pushing it to 0, 0, because C2 has no syndromes. And similarly, you have X1. X1, after X1, you can have C2, or you can have X2. Okay. Let us, for simplicity concern, we will ignore the X1, C2, but that also should be considered. Let us focus on X1, X2. So what happens to X1, X2? So if you have an error X1, X2, this will be 0 and this will be 1. So it will push it to another node which corresponds to 0, 1 at this stage. Okay. And now you have X3. So X3 will push it to 0, 0 back. So because X1, X2, X3, if I think about that here, that will give you 0 syndrome and 0 syndrome. X1, X2, there are 2 anti-commuting components. So that becomes commuting. If the X1, X3, there are 2 anti-commuting components, so they commute. And similarly, you draw a path from here to here, because you apply C3, that is not going to do anything. So in the end of the day, I wanted all paths that starts from the syndrome 0, 0, ends at syndrome 0. I try to do for other things also. Like now here I apply X and C. Similarly, I can apply Y too. So in this case, Y will push me here, and identity will push me here. And here, if I apply Y or identity, it will push to different places accordingly. It may push to a different syndromes and so on. Okay. And you focus on all the connections that start from syndrome 0, 0 to syndrome 0, 0. So you take that path. Okay. So for example, for simplicity, I am trying to use this path. So I have these 2 paths. So I am considering only 2 paths for the time being. So this one is X1, X2, X3, and this is C1, C2, C3. So I talk about 0, 0, 0, 0, 0, 0, 0, 0. This will be 1, 1, and this will be 1, 0. I talk about only this. And remember, there are other paths too. Okay, there are other paths too. Okay. So how this decoding works? Once the syndrome is obtained, we obtain a bogus Pauli operator, bogus error operator, such that this error operator will give you this syndrome. That is, your H times lambda, this E transpose equal to S. Okay. So you construct the bogus error operator E. Okay, so you find the operator, and this can be computed fast. So this doesn't require exponential complexity or so on. It requires the complexity of finding this E. Can be arbitrary. This can be any error that satisfies H lambda times E transpose should be equal to S. So this can be computed in a linear complexity. Okay, so we need not worry much about the complexity. This can be found out by linear complexity, like any. So it's not specific. Any can be found out by linear complexity. Now, once you find out this arbitrary E, for example, say you have found out an E that says that X1 identity. So let us say, for example, this is this one. Then what you do is you construct something called a shifted trellis. So what I do, I just multiply this with all the edges. So earlier I had C1. Now I multiply with X1. So C1 times X1. So earlier I had C2 here. I multiply with identity. C2 times identity. So earlier I had C3 here. I multiply with identity. Now I don't worry about the nodes. Like I don't worry about these numbers. These are not very significant here. Those are significant in the sense that they are useful for constructing the trellis and not the decoder. And from here, so you have X1 already in this edge, corresponding to this edge. Now this error will give you one X1. So X1 times X1. So you do that. And this will be equal to identity. And this will be equal to proportional to Y1. And then you apply, you have X2 here, X2 times identity. So here you have the identity as a second operator. So you apply identity here. And you have X3 here, X3 times the third operator, which is third operator is also identity. So you construct the shifted trellis. So this one is a shifted trellis. Now, once you construct the shifted trellis, the end goal is to find an optimal path from this node to this node. That will give you the error estimate. So if I say this is the optimal path, then my error estimate is Y1, C2, C3. This will be my error estimate corresponding to this syndrome. Yeah.
Sorry for the interruption. Your content is not visible.
Oh, okay.
I'm
now
able
it
to
is
see a slide.
yeah,
I'm able to
it's
see.
okay. Yes, sir.
Oh, sorry. Okay. Then I stopped sharing. Okay, I will share it again. So did I stop sharing?
Now it is, now the entire screen is visible. Yeah, now the entire screen is visible.
Visible, right?
Yeah. Now your slide is visible. Yeah.
Visible, right? Okay. Oh, okay. So do you have any questions? Like, should I repeat anything?
No need, sir.
Okay, fine. So the thing is, I construct this shifted trellis, okay, and then I wanted to find the optimal path. Like, so normally the challenge is in finding the optimality. So which is optimal? So I don't define optimal here, but usually the optimal will be in the sense of minimum weight or maximum likelihood. Okay, so minimum weight in the sense minimum number of non-identity operators or maximum likelihood, which is like we try to compute the probability of each error and we say which error is highly likely to be occurred in this particular channel given the syndrome. Okay? So we try to find that and we choose that error, and that can be found out using this repetition, this particular trellis. And in this trellis, that optimality is finding the optimal path from this node to this node. And to find the optimal path, we need to some processing at all these nodes, intermediate nodes. So the processing, how it works, you start from the initial node and you go to the remaining nodes as such. And whenever there are two paths that is reaching a node, like for example, for this node, when we come to this stage 3, for this node, there are two paths, this and this. Whenever this happens, we pick one path which is optimal and exclude the remaining path. So in that way, we don't try to focus on all the paths from this origin to destination, but we will focus on only the selected path. We discard the path at each cycle. So the complexity is reduced heavily. Okay. But so you discard this path and you have this path. And end of the day, you will have two paths connecting here. So you discard one of the path and you retain only the optimal path. Okay. So the goal is like finally you find this optimal path and you see the operators that is in this optimal path. And then you call this error as the optimal, the best error estimate for this particular syndrome. That is the whole idea of trellis decoder. Okay, and the trellis decoder should be optimal usually, but in this case it is not that optimal. But then it is better than our. It can be made better than our belief propagation decoders. But the advantage in belief propagation decoders is this belief propagation decoders are the complexity wise they are faster, but this trellis decoders, the complexity wise exponential. So I can show you some slides about trellis decoders. So can you see the slides? The slides are visible, right?
Yes.
So I am trying to show a different slide. So where so we have a syndrome trellis. I tried to show you the syndrome trellis based on certain error. So this is for a different error correction code, and our goal is to find an optimal path from all zeros to this from the origin node to destination node. Okay, but then the complexity is exponential, because if you see at each stage, so here I have one edge, here I will have two edges to be processing. And the number of nodes I am supposed to process here, that is proportional to the number of non-zero syndromes. So you have 0, 0, 0. So at worst case, it can go up to 1, 1, 1. So you will have 2 power 15 nodes at one level itself. So your complexity goes towards exponential, though it's not exponential. Like it is still exponential. Sorry, it's not as exponential as finding the brute force method, like finding the optimal solution using brute force method. I will try to show the numerics there, like so. And so, but again, apart from that, if we have more memory, if we have a sufficient memory to compute our algorithm, then we can process our algorithm in parallel. Like so, for example, in this case, if you can see the patterns repeats. So if you see this, the same X pattern repeats here. Here also you have the same. So if you know DFT algorithm, this looks like a butterfly pattern. So the same pattern repeats. And usually if you see the same pattern repeats in trellis decoder, this can be proved in one of our papers. And even if you go for a bigger error correction code, you can observe that the pattern repeats. You see here. So in these places, the pattern repeats, but it may not be clearly visible. But here you can see the pattern here and pattern here are same. So we can exploit this similarity in these patterns and the parallelism in the processing. Like for example, if I want to process this node, I don't have to worry about processing on these nodes. Like it depends on the input on the previous stage. So I can process this node and this node and this node, all the nodes in this level in parallel. So if I have enough computational power, like if I have enough computational capability with enough RAM, then I can do this decoding in parallel. And thus I can make it linear in terms of time. But then in terms of space, the complexity becomes exponential. That is a challenge that we will face when we try to implement trellis decoder. But the advantage of the trellis decoder is there are slight modification. If you do on trellis decoder, this can become the optimal decoder instead of the brute force. This one will be better, faster than brute force. But then it is much more slower than the belief propagation decoders, which are polynomial speed. Like, okay, so this is some numerics to show. Like we worked out the numerics for certain error correction codes, and you can see this yellow line and a blue line. This blue line represents an exponential the complexity in the sense of which is proportional to d, okay, distance of the code. And if you see distance, all the codes that we picked up, the distance is square root of n usually. Okay, so if you see here, so most of our points lies between this d to d. So they are not going towards n. So they are not exponential in terms of n, but they are exponential in terms of root n in these cases. They are proportional to, these are not theoretically proven that they are close to 2D, but these are for these particular examples, we got this number of computational requirement. Okay, so the takeaway is trellis decoder, it reduces the complexity, but in terms of performance, so far we didn't make it optimal, but it can be made optimal. And but in terms of other decoders like belief propagation or union find, there are other decoders like union find, belief propagation, which are polynomial time or close to linear time and so on. And those are easily implementable, but they are not very optimal decoders in the sense like it. but for time being, people work on those because they are easily implementable and they are sufficiently good enough. Like the performance is not too bad. Like they are very close to the optimal decoders. Okay. And so as of now, we are looking into some of the problems related to this trellis decoder. We are trying, so apart from code construction, we are trying to see whether this trellis decoders can be made practical and using several extra techniques. And we are also looking into see whether we can construct codes which are good for trellis decoders other than the convolution codes. Okay, convolution codes are a separate class of codes. We are trying to look into this linear block codes which are good for trellis decoders, and also there are things that we are looking into see whether we can do trellis decoders for measurement errors. These are some of the problems that we try to address, like in terms of trellis decoders. Okay, so is that fine? Like uh, so there are some other decoders which I am not, which I am planning to skip here. So in this slides, so I have made some interesting decoders, which are based on classical erasure correction or classical peeling decoder. It is called peeling decoder because the way we peel the objects, the decoder works like that. You start with some point and we go to its boundary. It will be something like this. The decoder works like this. So we start with some random point and we grow it accordingly. And then once we grow it further, we try to peel it. So for now, this decoder will not be clear for anyone because I'm not planning to explain this decoder, so because of time constraints. Okay. So if you are interested, you can go over and try to see this peeling decoders and belief propagation decoders. So these are some class of decoders that people from classical error correction codes or classical computer science background, they can start looking into. Okay, and the other type of problems that people can work on is on code construction. So we wanted code construction that supports something called fault tolerance. Probably in tomorrow's talk, you will be introduced to fault tolerance. So we need codes that satisfy all those conditions that we have discussed now. Like we need H such that Hx times H is a transpose equal to 0 and so on. But then we need something more than this simple error corrections, and that is what we call it as fault tolerance, and that will be discussed in the forthcoming talks. Okay, and so with this I will stop my discussion on error correction codes. Then after this I will try to introduce something on algorithms. Okay, so if you have any questions so far, you can clarify that.
So I just have one query. So just like we are using this classical like quantum LDPC, quantum polar. So like are any of these quantum codes that are originally designed for the quantum technologies from this, do people take inspiration and use it in the classical setting or anything?
For now, so there are no codes.
Okay.
So one of the challenge here is a quantum code which is good for quantum computers is a bad code for classical codes.
Okay. What is the reason? The complexity?
So the reason is the main reason is we wanted H is a transpose equal to 0. So what does it mean? It means if I take a row H1, like an element from H is, okay, that is in the row of Hz, my Hx times H1 transpose should be equal to 0, which means from the classical sense, my H1 should be a code word that is constructed by Hx. Okay, and now in quantum sense, if I want a better codes, I wanted my Hz to be of low weight. To the elements of H, the row elements of Hz to be of low weight, because I wanted that low density. This, if I wanted this LDPC structure, I wanted this H1 transpose to be of low weight. Okay, and classically, if you have a code word of low weight, then that is a very bad code, right? So we don't call that as a very good code. Like that has a very severe issues. in terms of this thing.
Okay.
So that will pull the minimum distance down, something called as minimum distance down. Minimum distance is actually represent the error correction capability of the error correction code. So pulling it down is very bad for it's bad for classical error correction code.
So the
Like from
Hadamard
the
distance. Hadamard distance.
from the sense, yeah.
Hadamard distance will come down.
Yeah, minimum weight or having distance will come down. Okay, so that will that's a so from the perspective of noise reduction, it is a bad thing for classical error correction codes. So people, so a good quantum error correction. So that's why I use the statement: a good quantum error correction code is a bad classical error correction. Right?
Thank you.
So any other questions? Okay, so maybe I have 40 more minutes. I will just try to introduce one algorithm that helps us to, at least I will try to align with our error correction talk so that it can be complete. So I will try to talk about one algorithm which helps us to estimate the syndrome. So throughout the talk, I told you that if we have a syndrome, like if we have a stabilizer, SN stabilizer, what we do is you have a received state where phi is the quantum state psi, the actual code word psi acted up with an error, like so some error E applied on the psi, the quantum state psi, and this E can happen because of some noise. Okay, so we are not worried for now. We are not defining what noise is and so on. We are just telling that it is some error. So suppose my phi, a new state, I obtained a new state phi which have an error E times psi, and then what we do is we try to compute whether S times psi equal to plus phi or minus phi. We try to compute this sign, and this is what will give you my this symbol E transpose equal to this one. It is 0 for plus sign and 1 for minus sign. This we talked about it. But then now the problem that we will try to address now is how are we going to estimate this? Can we estimate this particular thing? And there are various techniques, but I will start with a simple thing which motivates us to think that it can be done. Okay, so there are fault tolerant protocols which helps us to estimate this, but in this talk I will try to introduce a simple algorithm which helps us to estimate this. Okay, so before going into the simple algorithm, we will try to focus on certain properties of quantum gates. Okay, so quantum gates we will focus on, so our focus is mostly on Pauli operators I, X, Y and C, and all operators that is generated by these 4 single qubit operators. All operators generated by this means, so I have, say for example, if I have 4 qubits, then I will talk about X on first qubit, I, this is one operator, and identity X, identity, this is another operator, and so on. There are so many operators that can be constructed by combination of these 4 Pauli operators on each of these qubits. Okay, so for us, our quantum stabilizer codes are going to correct errors of this type, and our stabilizers also belongs to this class. So it also belongs to Pauli operators of n qubit type. Okay, so now how can we do this construction? And the first point here is S times phi will be equal to either plus phi or minus phi. So this is the key catch here. Okay, so what we do here, we construct a new quantum state which is initiated by 0, and we apply a Hadamard gate to it. Okay, and the outcome of this Hadamard gate h times 0 will be equal to 0 plus 1 by root 2. So I hope you might have gone through the what Hadamard gate is. So Hadamard gate is a 2 qubit Pauli gate which is represented by this matrix. Okay, this matrix. So if I try to apply Hadamard on 0, I will end up getting something like this. Okay, so this can be seen by h times 1 0 should be equal to 1 by root 2 times 1, 1. So 1 by root 2 times 1, 1. So you have 1, 1. So you have the coefficients accordingly. Okay. So you apply a Hadamard gate, and then on the other side, you put my phi. So here I will have n qubits. So though my line is one line, we are having n qubits. Okay. And then what you do is you apply a control stabilizer operator. Okay. So you apply a control stabilizer operator, and then you apply a H here, and then do the measurement. Okay. Now I will talk about what control stabilizer operator is. So control stabilizer operator. So I have phi. Okay. So this one, what it does is whenever I have 0 and phi, whenever my first state is sorry. Okay. So whenever we have 0 tensor phi, this will be translated to 0 tensor phi. Whenever I have 1 tensor phi, so whenever this is 1, I apply a Hadamard gate on the, I apply the stabilizer on the second qubit. So 1 S times phi. This is this control gate. This control gate. This is the action of this control gate. Okay. So that is something that we try to exploit it here. So now if I apply Hadamard gate here, so what happens here is at this stage, so whatever we have is 0 phi plus 1 times phi by root 2. So the second qubit is phi, okay, and the first qubit will be 0 plus 1 by root 2. That is Hadamard acting on. The first qubit is 0 plus 1 by root 2, and the second qubit is phi, and that will be translated as something like this. And now once I apply this control S gate, so here what happens is whenever the first qubit is 0, you don't do anything on the second qubit, and whenever the first qubit is 1, you apply this whatever gate you have here, you apply the S gate here by root 2. Okay. Now there are two cases as we discussed earlier. Now S times psi will be equal to psi, or S times phi will be equal to minus phi. Okay. So this can become something like 0 phi plus 1 times phi by root 2. Okay. Or that is whenever my S times phi equal to phi, I get this, or whenever my S times phi equal to minus phi, I get this 0 phi plus 1 times, okay, sorry, this one becomes minus times phi by root 2. So you get a negative sign. So whenever S times phi equal to psi, I end up getting this. Whenever my S times phi equal to minus phi, I end up getting this. Okay. So this one will be S times phi will be equal to minus phi. Okay. And this is equal to, if you keenly observe, you can take phi outside. So this becomes exactly equal to 0 plus 1 by root 2 tensor product with phi, and this one will be exactly equal to 0 minus 1 by root 2 tensor product with phi. Okay. So in this case, now if you apply Hadamard is equal to 1 by root 2 times 1, 1, 1 minus 1. And if I apply this Hadamard on the first qubit here, so if I apply Hadamard on 1 by root 2, 1 by root 2, this one will give you 1, 0. You can cross check this computation. So if I have Hadamard on 1 by root 2 minus 1 by root 2, this will yield you 0, 1, this vector. So this is equal to 0 and this is equal to 1. So if I apply Hadamard on the first qubit, this becomes 0 and phi. And if I apply or, this becomes 1, phi. Right? So whenever my S times phi equal to phi, this will be s times phi equal to phi, I end up getting this. Whenever my s times phi equal to minus phi, I end up getting this. I do the measurement on the first qubit, it's exactly a classical qubit. It becomes a classical qubit. I get either 0 or 1 according to the commutation relation. So in this circuit, I will exactly get my syndrome out of it. Okay. So this is a proof to say that, okay, there exists quantum algorithm to extract this value, whether it is +1 or -1, that can be extracted using this particular circuit. Is that fine? And this particular circuit is so do you have any questions on this? Like, so if I have to stop it. Okay. So to continue it, so this particular circuit, it can be generalized as something called a phase estimation. So quantum phase estimation, quantum phase estimation, and a generalization of that. So you have some arbitrary unitary operator, and you take one qubit, and you have a control U. You pass from psi, and you do this the same operation Hadamard and Hadamard, and you do the measurement here, and then you will get one bit of the eigenvalue corresponding to lambda. So suppose if I try to find the eigenvalues of u, that is u. So suppose there exists a vector u times x equal to lambda times x. Okay, and if since u is a unitary operator, my lambda will be of the form e power I some phi, where phi is some angle, phi, or u power I times phi, where phi will be some 0.I1, I2 or something, like some integer like this. Okay? And this one will give you the first element from this. Yeah, so again e power I phi, so you end up getting 2 pi. Okay, your phi can be of this range. In the binary form, it will be of 0.I1, I2, and so on. Now, this particular circuit will help you to find out the first decimal point after first binary number after this decimal point. That is, it will help you to find I1. Now, to find I2, what we normally do is you apply U square here. If I do apply U square, then you to some extent you get the second decimal point, that is I2, the term, because if I apply U square, the eigenvalues of U square will be lambda square, which means e power I phi times 4 pi, which means e power I 2 phi times 2 phi, and this is phi, means your 2 phi will be I1 points I2 and so on, and this term I1, since it's an integer, so e power I 2 power 1 will be equal to 1, so that fades away, that won't show up. So by this kind of operation, you can estimate I2, and similarly you apply u power 4, you get I3, and so on. Okay, and the bigger picture of the circuit will be something like this. You have some k qubits, and you have apply Hadamard gate on all those k qubits, and these qubits are initialized with 0 k qubits, and you have a control unitary, a sequence of control unitary, that is control unitary and control unitary square and so on. Okay, and then instead of Hadamard gate, to be little more efficient, instead of Hadamard gate, we use something called as inverse quantum Fourier transform. Okay, and this quantum Fourier transform is nothing but the discrete Fourier, the quantum version of this discrete Fourier transform. So if you know discrete Fourier transform and this quantum Fourier transform, your quantum Fourier transform, the matrix will be something similar to that discrete Fourier transform, that is 1 by root n. You have 1, 1, 1, 1, 1, the nth root of unity, wn power 1 and wn power 2 and so on, wn power n, and 1 wn power 2, wn power 4 and so on. and 1 wn power 3, wn power 6, and so on and so on. So this is exactly your DFT matrix, but except that we, in this particular DFT, the kernel that we use is 1 by root n times matrix, because I wanted the QFT to be unitary matrix. Okay, and so we try to use this, and we can estimate the eigenvalues of arbitrary unitary matrix. Okay, so given a unitary, and as you know, this finding eigenvalues is used in many applications. Okay, and
here
this
also
is
you
what,
have that butterfly diagram for FFT for faster implementation.
the only problem here is we are going to define QFT as a QFT matrix, because the QFT acts on quantum state. Unlike the classical sense, if I take a vector, say length 4 vector, so you have A, B, C, D. Now A can be separated out. If A can be taken out separately, B can be taken out separately, C can be taken out separately, and D can be taken out separately. But in quantum sense, we cannot take A, B, C, D separately. So classically, since we can take A, B, C, D separately, we can do the butterfly structure and apply A, B and do A plus B into some term, something so on, right? So you take, A, B, and B. This can be helpful in terms of numerical implementation of the quantum algorithm, like the implementation of the quantum algorithm in the classical computers. In those sense, this can be implemented using this butterfly architecture and so on. But when I talk about just quantum Fourier transform, this cannot be implemented using the same butterfly architecture that we see in classical code, classical DFT. But instead, we will have a sequence of quantum operation which help us to implement this quantum Fourier transform. Okay.
Okay. Thank you.
Okay. So maybe if I start a new topic on algorithms, it may take more time. So if you have any questions, you can clarify that now. And otherwise, maybe we can wind it up. So if you have any questions, you can clarify now. So otherwise, maybe we can, someone has asked a question. How can we implement this error coding with a security application? Could you please list some real-time examples? Okay. So the applications of quantum technologies is twofold, like to be specific. So if you talk about applications of quantum algorithms, at least the primary goals are twofold. The first one is security, and the second one is fast computing. Okay. So one particular example is there is something called Groover's algorithm. So which helps us to suppose you have a database of n elements. So say for example you have a list of students and their mark list or roll numbers or something like that. You have a list of students in your classroom or something like that. Okay, and suppose the number of students is so high, say something like 10 of order of 10 power 4, 10 power 5, and it's very big. And now I wanted to find a student with say roll number particular K or roll number R. Okay, so if I want to find a student with roll number R, what will we do from a classical perspective? Or if I want to find a student with certain characteristics, what will I? Classical perspective, I will go into each and check the roll number. Or if the list is ordered, if the roll numbers are ordered, if your students are from the same batch and same classroom, maybe the roll numbers will be ordered. So you can directly see the roll numbers from 1 to by just seeing R, you can find out the student's name or something like that. But suppose if the ordering is not proper, if there is no proper ordering, you don't order them according to their roll numbers or numbers, maybe random roll numbers or some sense of random ordering is there. Then if I wanted to search one student with a particular roll number, the best thing that I can do is I will go to each student and find out whether this student belongs to this roll number or not from the classical sense. So the computation complexity, worst case computation complexity is proportional to the number of students you have. Okay, so that's the worst case complexity in the sense of classical algorithm. Now, suppose you can implement a quantum algorithm, which if you give the student, if you give the roll number, the algorithm will find out, like, so for example, you have some oracle, some random circuit, so random quantum circuit, which tells you, like, if you give the roll number and the student's name, okay, you give the roll number and student's name, it should give you that match. It will tell you that this roll number is belongs to that particular student. It will tell you, it should be able to verify it. Suppose you have a problem that is easily verifiable, okay, so then what you can do is you can construct, easily verifiable means it can be verified by a quantum circuit. If you can verify that, then you can construct a quantum algorithm which is based on this Groover search algorithm, in which the computational complexity can be improved to root n. And if you see most of the public key crypto system algorithms, these in the earlier, like most of this public key crypto system algorithm, their security relies on this. So how does their security relies on this? Like, so, sorry, most of the private key crypto system, their security relies on this complexity. So suppose I make a key of, say, 64 bits. Someone who wanted to find out my key, and if I make it random enough, if I make a random key which is random enough for 64 bits, then I have to go for 2 power 64 options, which is too high for my capability. Like 2 power 64 is too high, right? But if I have a quantum computer which can verify whether my key is a valid key or not, which can nicely apply my key and see whether my result is meaningful or not, in that case, I don't want to go for this 2 power 64 computation. Instead, I can do it in 2 power 32 computation itself. It is far faster. Like, instead of 2 power 64, you do with 2 power 32. Okay, and it's not right, far half, yes, right. So to make an analogy, when suppose you have a 8-bit key, so you will have 2 power 8 possible keys, which means something like 256 or something, right? This can be searched by using just 2 power 4 searches, which is proportional to 2 power 4 searches. So which is something like 2 power 4 is something like 16. So you have a size of 256 search space, but you can do it in 16 individual searches, so which makes it faster. So now my private key crypto system, the security relies on this. As my key length is higher, my search space is higher. Like, so I have to search a longer time. So if someone wanted to find out my key, he will take a longer time, before which I can change my key. So the key can be altered by using some other randomness. Okay, so that is the whole idea of this private key crypto system. But now, because of this speed up from n to root n, now we are forced to improve the key size. So we cannot have, so suppose earlier, whatever the system that is strong with respect to 64-bit, now it is strong with 128 bits. Whatever is strong with 128 bits is strong with the 256 bits, and not strong with 128 bits. It becomes weaker. Okay, so that is one challenge that comes out of this Groover's algorithm. And there is another algorithm which we call it as Shor's algorithm. Okay, so Shor's factoring algorithm, which claims that, okay, I can factor any big prime. You give a very big prime number, which is, sorry, a very big composite number, which is of n equal to p times q, where p and q are two prime numbers. And now if you can, I can find P and Q in linear time, in a reasonable time. Okay, I can find P and Q in a reasonable time. That's the idea. And why is this problem for us? For some of this algorithms like RSA algorithm, they relies on this security, like this security. Like, so if you have a very large number P and Q, and if you are given n equal to PQ in public, and then it's very hard to decompose. It's very hard to find P and Q given n. So that is the challenge. That is the place where our RSA crypto systems or older crypto systems are secure. But now, because of this Shor's algorithm, which makes factoring faster, all our crypto system becomes under threat. Like, so our crypto system is threatful. Okay, and so fast computing is completely a different sense of security. But the fast computing is a challenge for a security. It's a challenge for the security because all our classical security relies on the lower computational power we have. Okay, and whatever we talked so far is something that helps this fast computing. All these error correction codes that is going to help these quantum computers, which are going to implement your algorithms here in a faster way. Okay, and this fast computing will help you in many ways, in the sense of faster implementation of machine learning algorithms, or faster implementation of some algorithms that are like classically hard and with some certain structure. Not all classical algorithms can be fastened, but there are classical algorithms with some certain structure which can be fastened using this quantum computer. And the quantum error correction codes that we talked about in this talk, all these are useful for this fast quantum computing and not security. We didn't talk about security at all in this talk. Okay, security is actually completely a different aspect, where people talk about two versions of security. One is quantum security, and another is something called as post-quantum security. And this class of algorithms, security class of algorithms, they are helpful to improve the security. So here we talked about Shor's factoring, which attacks security, and similarly Grover's algorithms, which attack security. And these security algorithms are going to help you in improving the security, with even if these attacks exist. Okay, and if you clearly say this post quantum security is actually a classical algorithm, so that is called as PQC, or post quantum cryptography. That is completely a classical algorithm which is implemented in a classical computer. But then the purpose of this algorithms is to defend our classical systems from these two attacks, the Shor's factoring attack and this Grover's attack. So that is the whole purpose of this post-quantum cryptography. And there is something called quantum cryptography, like that is helpful in the sense that they use quantum principles, that is, the qubit cannot be copied and so on. Okay, and for now we didn't talk much about how error correction codes can be merged, like it can be merged with the security applications. That requires some more detailed discussion, but there are not sufficient work on that directions too. Like, for now there are connections between classical error correction codes to this security applications. Okay? That will require a little more time for introducing the security. So here we use classical error correction codes when it comes to this both the post quantum security and both quantum security. They use quantum this classical error correction codes and not quantum error correction codes. Okay, and at least to my knowledge there is no connection, so no applications of quantum error correction codes with respect to quantum security for now. Like, so there can be something that can be connected, but for now I don't know any study related to this, or I didn't try to explore studies related to this. Okay. And any other questions? So what is this question? Processing will take a long time. I didn't get that question. So is it related to this talk, or is it something related to that attendance or something?
No, actually, while you were taking about that shortest path, optimal path, that time I was posting that question, sir.
Oh, okay. So for now, that decoding algorithm is time consuming. It is not a very practical decoding algorithm. That the trellis-based decoder that I talked about is not a very practical decoder, but we are studying that for finding interesting connections. So the one aspect we are trying to make it practical, but that is highly challenging. Like we don't see a fruitful solution there, but still we are trying to see whether we can make it practical or not. But the most interesting aspect is it is useful to understand the quantum error correction code, understand how quantum error correction codes work. So those are the places where it works. Otherwise, we wanted a decoder which works faster. We don't. If you rely on these decoders, when we go for, we wanted faster computation and slower decoders, that is actually counter intuitive. Like that's both are in opposite direction. So that's a, like we don't implement it as a error correction code for this quantum computers, but we study that because we are seeing whether that can be done. That is one direction, and second direction is and most fruitful direction is we are trying to understand the existing quantum error correction code using this structure. So that will helpful in understanding the quantum error correction code and constructing more and more good quantum error correction codes in a faster way.
Okay, sir. Thank you.
So anything else? So what is the difference between post-quantum and quantum classical codes? So yeah. So I hope I was talking about that. So there is nothing like when you talk about classical error correction code, there is nothing like post-quantum and quantum. So this word post-quantum comes with respect to, especially in the sense of cryptography. Okay. So these are not, so the cryptographic codes are not error correction codes. They are like a different version of error correction codes, but then they use the tools of error correction codes, like your parity check matrix or the classical understanding of classical codes. So they try to utilize this classical codes and modify it little bit to get a get a cryptographic algorithm. Okay. So they are not like explicitly connected to quantum error correction codes, but they use this theory of quantum error correction codes to construct the post quantum cryptography. Sorry, again I made a mistake. I should not use the word quantum error correction. So I wanted to stick to classical error correction when I talk about cryptography. Okay. So for example, when I talk about post quantum like key distribution, quantum key distribution. So if I talk about quantum key distribution, the thing is, first we pass some quantum information, okay, from user A to user B. So they share. So the purpose of quantum key distribution is to share a classical key between user A and user B. So the goal is I wanted to share a common key K with the user A and user B, such that the third party cannot find out what the key is. So this is something similar to the application of public key crypto system. The main purpose of public key crypto system is usually to share a private key. Will be the main goal usually. Like that is one of the main goals. Like, yeah, that is one of the main goals. So here we try to share a common key between user A and user B using quantum key distribution. Here what we do is we pass some quantum information, or we share some quantum information between user A and user B, and from using the shared information between user A and user B, they extract this key. Okay, I'm not going to give the details again, it will take a longer time, but the goal is to extract this key, the value of key. But then this key will not be fully good enough. Like it has noise. Like again, it passes through the channel, so it has noise. So it passes through noise, and again there will be some information leakage from this quantum information in practical sense. Though theoretically they are perfectly secure, from practical sense there will be some leakages. So we have to improve the security and improve the uh, reliability of this key. For that purpose, we use classical error correction code. error correction codes to improve the reliability of this key. And there is something called hashing. So this is some cryptographic term. People who are working in cryptography, they know what hashing is. But my focus is on error correction code. This error correction code is used to improve the reliability of this key, and hashing is usually used to improve the security of the key. And this error correction code is exactly a classical error correction code, because this is acting this key and not the quantum information. It's acting purely on my key and not the quantum information. And on the other side, we have this post quantum cryptography, and there is something called code-based crypto system. Okay, so for now I don't remember this definition well, but in this case the overall idea is you pick up like you apply a nominal error to your code words, actual code words supposed to be sent, that the key that is supposed to be shared, you apply a nominal error, that is h times e. And the challenge here is how feasible to decode this h times e plus e. That is the challenge in the that is where the security will be. And this e will be nicely constructed so that the complexity of decoding h times c plus e will be heavier. It is not as simple as error correction code decoding. It should be a little more heavier. Okay. For now, I don't know the complete detail, but this is the very vague idea of code-based crypto systems. And that is how error correction code is used in classical crypto, in post-quantum cryptography. So here again, this H is the parity check matrix corresponding to a classical code. Okay, all these things like that. So is that fine? Like any other questions?
Yeah, thank you, Dr. Arun, for spending nearly 3 hours giving us this beautiful lectures, which was towards the end, it was also very broad, and also you went very deep in the math. So it was very, very useful and to learn new things. Thanks a lot.
Yeah, so I hope it motivates someone, and so that they can pursue further, and rather than like, so I aimed at motivating people. That's it. And there is one more question: how can we implement same QKD for laser-based communication? I don't know, sir. Like, so sorry, I don't know much about how to implement this crypto system on laser-based communications or something. Yeah, so thank you for inviting me. I hope it is fruitful for uh, at least many of you, or at least some of you. And I hope I have motivated enough people in this direction. And again, you may have few more sessions on quantum error correction code. I hope this will be helpful to understand those sessions also. And if you have any questions or anything, you feel free to contact me. So my screen is under sharing, right? So am I?
Your screen is visible.
Sharing?
Yeah. You can write your
Visible, right?
email ID.
If you are feel free to contact me if you have any questions further. My email ID is aloysius@iitg.ac.in. Okay. Yeah, probably this one will help. Like, so somewhere here it is there. So this one will help. Like, so if you are interested in working with me, or if you have any questions, you are feel free to uh, share me anything through this email ID, and I am happy to interact with people in the sense, like I can learn, and I I can learn more by more interaction, like, than reading books or watching lectures. Right? Yeah, I'll be happy to interact. Yeah, please feel free to email me if you have any questions.
Yeah, thank you, Dr. Arun. I think you can close the session. Yeah, thanks a
Okay,
lot.
thanks.
Thank you. Thanks for your time. Yeah. Yeah, so the participants, thank you for attending a second day. So if you have any problem in attendance, you just email me or you just drop me a message in WhatsApp. If you're not, I think others were able, many people were able to put their attendance, but I think some of you have some issues. I have not seen the chat, but if you have any problem, you just email me or you message me in WhatsApp. Okay. Thank you. We'll meet tomorrow at 6 o'clock. Thank you. Tomorrow also same link. So I have sent you the invite or your email. This link you will receive in the afternoon. So you can accept that. Then you won't need to wait in the lobby. You'll be directly allowed to enter in. So the last email I sent you in the afternoon, you can try to accept that. Thank you.
Thank you, sir. Thank you so much.